This video introduces functions and their domains and ranges. A function is a correspondence between input numbers, usually the x values, and output numbers, usually the y values, that sends each input number to exactly one output number. Sometimes a function is thought of as a rule or machine in which you can feed in x values as input and get out y values as output. So a non-mathematical example of a function might be the biological mother function, which takes as input any person and gives as output their biological mother. This function satisfies the condition that each input number or object, person in this case, gets sent to exactly one output person, because if you take any person, they just have one biological mother. So that rule does give you a function, but if I change things around and just use the mother function, which sends to each person their mother, that's no longer going to be a function, because there are some people who have more than one mother, right? They could have a biological mother and adopted mother, or a mother and a stepmother, or any number of situations. So since there's at least some people who you would put it as input and then you'd get like more than one possible output, that violates this rule of functions. It would not be a function. Now, most of the time, we'll work with functions that are described with equations, not in terms of mothers. So, for example, we could have the function y equals x squared plus 1. This can also be written as f of x equals x squared plus 1. Here, f of x is function notation that stands for the output value of y. Notice that this notation is not representing multiplication. We're not multiplying f by x. Instead, we're going to be putting in a value for x as input and getting out a value of f of x or y. For example, if we want to evaluate f of 2, we're plugging in 2 as input for x, either in this equation or in that equation, since f of 2 means 2 squared plus 1, f of 2 is going to equal 5. Similarly, f of 5 means I plug in 5 for x, so that's going to be 5 squared plus 1, or 26. Sometimes it's useful to evaluate a function on a more complicated expression involving other variables. In this case, remember, the function's value on any expression is just what you get when you plug in that whole expression for x. So f of a plus 3 is going to be the quantity a plus 3 squared plus 1. We could rewrite that as a squared plus 6a plus 9 plus 1, or a squared plus 6a plus 10. When evaluating a function on a complex expression, it's important to keep the parentheses when you plug in for x. That way, you evaluate the function on the whole expression. For example, it would be wrong to write f of a plus 3 equals a plus 3 squared plus 1 without the parentheses, because that would imply we were just squaring the 3 and not the whole expression a plus 3. Sometimes a function is described with a graph instead of an equation. In this example, this graph is supposed to represent the function g of x. Not all graphs actually represent functions. For example, the graph of a circle doesn't represent a function. That's because the graph of a circle violates the vertical line test. You can draw a vertical line and it'll intersect the graph in more than one point. But our graph at left satisfies the vertical line test. Any vertical line intersects the graph in at most one point. That means it's a function because every x value will have at most one y value that corresponds to it. Let's evaluate g of 2. Note that 2 is an x value, and we'll use the graph to find the corresponding y value. So I look for 2 on the x-axis and find the point on the graph that has that x value. It's right here. Now I can look at the y value of that point, looks like 3, and therefore g of 2 is equal to 3. If I try to do the same thing to evaluate g of 5, I run into trouble. 5 is an x value, I look for it on the x-axis, but there's no point on the graph that has that x value. Therefore, g of 5 is undefined, or we can say it does not exist. The question of what x values and y values make sense for a function leads us to a discussion of domain and range. The domain of a function is all possible x values that make sense for that function. The range is the y values that make sense for the function. In this example, we saw that the x value of 5 didn't have a corresponding y value for this function, so the x value of 5 is not in the domain of our function g. To find the x values in the domain, we have to look at the x values that correspond to points on the graph. One way to do that is to take the shadow or projection of the graph onto the x-axis and see what x values are hit. It looks like we're hitting all x values starting at -8 and continuing up to 4. So our domain is the x's between -8 and 4, including those endpoints, or we can write this in interval notation as -8, 4 with square brackets. To find the range of the function, we look for the y values corresponding to points on this graph. We can do that by taking the shadow or projection of the graph onto the y-axis. We seem to be hitting all y values from -5 up through 3. So our range is y's between -5 and 3, or in interval notation, -5, 3 with square brackets. If we meet a function that's described as an equation instead of a graph, one way to find the domain and range are to graph the function. But it's often possible to find the domain, at least, more quickly by using algebraic considerations. We think about what x values it makes sense to plug into this expression and what x values need to be excluded because they make the algebraic expression impossible to evaluate. Specifically, to find the domain of a function, we need to exclude x values that make the denominator 0, since we can't divide by 0. We also need to exclude x values that make an expression inside a square root sign negative, since we can't take the square root of a negative number. In fact, we need to exclude values that make an expression inside any even root negative, because we can't take an even root of a negative number, even though we can take an odd root, like a cube root of a negative number. Later, when we look at logarithmic functions, we'll have some additional exclusions that we have to make. But for now, these two principles should handle all functions we'll see. So let's apply them to a couple examples. For the function in part A, we don't have any square root signs, but we do have a denominator. So we need to exclude x values that make the denominator 0. In other words, we need x squared minus 4x plus 3 to not be equal to 0. If we solve x squared minus 4x plus 3 equal to 0, we can do that by factoring, and that gives us x equals 3 or x equals 1, so we need to exclude these values. All other x values should be fine, so if I draw the number line, I can put on 1 and 3 and just dig out a hole at both of those, and my domain includes everything else on the number line. In interval notation, this means my domain is everything from -infinity to 1 together with everything from 1 to 3 together with everything from 3 to infinity. In this second example, we don't have any denominators to worry about, but we do have a square root sign. So we need to exclude any x values that make 3 minus 2x less than 0. In other words, we can include all x values for which 3 minus 2x is greater than or equal to 0. Solving that inequality gives us 3 is greater than or equal to 2x. In other words, x is less than or equal to 3/2. I can draw this on the number line or write it in interval notation. Notice that 3/2 is included, and that's because 3 minus 2x is allowed to be 0. I can take the square root of 0. It's just 0, and that's not a problem. Finally, let's look at a more complicated function that involves both a square root and a denominator. Now there are two things I need to worry about. I need the denominator to not be equal to 0, and I need the stuff inside the square root sign to be greater than or equal to 0. From our earlier work, we know that the first condition means that x is not equal to 3 and x is not equal to 1. And the second condition means that x is less than or equal to 3/2. Let's draw both of those conditions on the number line. X is not equal to 3 and x is not equal to 1 means we've got everything except those two dug out points. And the other condition, x is less than or equal to 3/2, means we can have 3/2 and everything to the left of it. Now to be in our domain and to be legit for our function, we need both of these conditions to be true. So I'm going to connect these conditions with an and. And that means we're looking for numbers on the number line that are colored both red and blue. So I'll draw that above in purple. So that's everything from 3/2 to 1. I have to dig out 1 because 1 was a problem for the denominator. And then I can continue for all the things that are colored both colors, red and blue. So my final domain is going to be, let's see, negative infinity up to but not including 1 together with 1 but not including it to 3/2, and I include 3/2 since that was colored both red and blue also. In this video, we talked about functions, how to evaluate them, and how to find domains and ranges. This video is a brief introduction to increasing and decreasing functions based on their graphs. In this first example, I've graphed two lines. The first line is an increasing function because as the x values go from left to right, the y values are going up. This can be written more formally by saying if x2 is bigger than x1, these are supposed to be x values, so that means that x2 is some x value that's to the right, so that it's bigger than x1. So whenever we have an x value x2 that's bigger than x1, increasing means that f of x2 has to be bigger than f of x1, so that the y values are getting bigger when the x values are bigger. The second line is an example of a decreasing function because here, as the x values increase from left to right, the y values are going down. So again, we can write this more formally by saying that whenever we have an x value, x2, that's bigger than x1, for example, this might be x2 and this might be x1, then the y value, f of x2, is less than f of x1 this time, because here, when we have a bigger x value, we want to have a smaller y value to be decreasing. This second example gives the graph of a function that's increasing in some places but decreasing in others. This part of the graph, here the function's decreasing because as the x values increase from left to right, the y values go down. Over here, we also have a part of the graph where the function is decreasing. Now, this part of the graph, the function is increasing because as x goes from left to right, the y values are going up. So I'll mark that one in green for increasing. And finally, on this part of the graph, the function's neither increasing nor decreasing. It's completely flat or constant. Now we're asked to describe the intervals on which the graph is increasing or decreasing, so we describe those intervals in terms of the x values. It wouldn't make sense to describe them in terms of the y values because the y values can be the same for different parts of the graph, but the x values are always unique. To describe where this function is decreasing, that's for x values between -4 and -2 and between 4 and 7. I can write this using inequalities as -4 less than x less than -2, 4 less than x less than 7. It's not important whether I use less than or equal to signs here. I'm going to use less than or equal to signs at the endpoints of the function's domain, where the function stops existing altogether, and I'll use strict less than signs just where the function starts or stops decreasing in the middle of its domain. But again, that's not important. To describe where the function is increasing, that's for x values in between -2 and 1. So I can write that as an inequality as -2 less than x less than 1. I can also describe these intervals in interval notation. So that would be close bracket -4, -2, open bracket, a cup sign for union, and then 4, 7 for the decreasing part, and the increasing part is -2, 1. I'm going to modify my graph just a little bit now by putting arrows on the end. When I have arrows instead of dots or just hard stops, that signifies that the function continues in the same direction forever. So if I write it like that, then the place where the function is increasing is still the same. It's still going to be from x values going from -2 to 1. But now the decreasing part of the function extends further. So this section, these x values extend all the way out to infinity, and we assume that it keeps going, it keeps decreasing here. So I would write that as for infinity, and similarly, the left part I would write as -infinity, -2, because the function is going on forever in this direction too, so the x values go all the way to -infinity on that chunk. So when talking about increasing and decreasing parts of functions based on graphs, the thing to remember is that x is going to be heading from left to right. As long as you do that, increasing just means that y goes up. Decreasing means that y goes down. And if you're describing the intervals, you have to do that in terms of x values. This video is about identifying maximums and minimums for functions from their graphs. We'll start with some definitions. A function f of x has an absolute maximum at the x value of x equals c if the y value at x equals c is as big as it ever gets. We can write this more precisely by saying that f of c, that's the y value at x equals c, is bigger than or equal to f of x, that's the y value at some other x value, for all x values in the domain of f. That biggest y value, f of c, is called the absolute maximum value for f. And the point with an x value and a y value given is called an absolute maximum point. If I have a graph of a function, then the absolute maximum value, f of c, is the highest value that function ever achieves, and the absolute maximum point is the point where it achieves that value. Now, it's possible for a function to have more than one absolute maximum point if there happens to be a tie where that highest value is achieved. But a function can only have at most one absolute maximum value. A function f of x has an absolute minimum at x equals c if the y value at x equals c is as small as it ever gets. We can write this more precisely by saying that f of c is less than or equal to f of x for all x values in the domain of f. The y value f of c is called the absolute minimum value of f, and the point c f of c is called an absolute minimum point. In the graph of f of x, f of c is now the lowest y value that the graph ever achieves, and the point c f of c is the point where it achieves this very low y value. For example, this function has an absolute minimum value of about -8. and it has an absolute minimum point with coordinates 3, -8. If this function stops here and has domain from x values just from 0 to 4, then the function will have an absolute maximum value of 10 achieved at the point with coordinates 4, 10. If, however, the function keeps going on forever, then it will have no absolute maximum value at all. Absolute maximum and minimum values can also be called global maximum and minimum values. A function f of x has a local maximum at x equals c if the y value at the x value of c is bigger than any y values nearby. It doesn't have to be the biggest y value anywhere in the domain. For example, for this function, there's bigger y values up here. It just has to be the biggest y value nearby, or more precisely, in an open interval of x values around c. We can write this by saying that f of c is bigger than or equal to f of x for all x values in an open interval around c. The y value, f of c, is called a local maximum value for f, and the point with coordinates c, f of c, is called a local maximum point. A function f of x has a local minimum at x equals c if f of c is less than or equal to f of x for all x values in an open interval around c. The y value f of c is called a local minimum value, and the point with coordinates c, f of c is called a local minimum point. A function might have many local minimum values. In this example, assuming that the domain is from 0 to 4, we have a local minimum point at x equals 3, because this point here is the lowest point anywhere nearby. It also happens to be an absolute minimum point. Turning our attention to local maximum points, this function has a local maximum point at 1, 2, say, because this point here is the highest point anywhere nearby, even though it's not the highest point anywhere in the domain, since they're higher points over here. So we have a local max point at 1, 2, which is not an absolute max. Different sources use different conventions as far as whether the point 4, 10 up here counts as a local maximum point or not. Some sources do consider it a local maximum, since it's the highest point anywhere nearby, but other sources say that it doesn't count as a local maximum for the technical reason that you can't get an open interval of values around 4, because the function's not defined in an open interval around 4, because its domain stops at 4. So I'll just write this as a caution that some sources do not consider 4, 10 to be a local max point because f is not defined in an open interval around x equals 4. Local maximum and minimum values can also be called relative maximum and minimum values. Please pause the video for a moment to mark all local maximum and minimum points on the graph of this function, as well as all absolute max and min points. The function has a local max point here, at the point with coordinates approximately, say, 2.7, 3.3. It's a local max point because it's the highest point anywhere nearby. There's a local min point right here at the point with coordinates 2, 2, since this is the lowest point anywhere nearby. If this point actually existed It would also be a local midpoint as well as an absolute midpoint, but this drilled out circle means that point is not actually part of the graph. So there's no local midpoint here, and no absolute midpoint. The point here, with coordinates 0, 4, is considered by some sources to be a local max point, but by other sources it's not considered a local max point, since the function is not defined in an open interval around 0. Turning our attention to absolute max and min points, well, there's no absolute max point since the function keeps going up and up and up forever. There's also no absolute min point because the function just keeps going down and down a little by little and never actually achieves a lowest value. Now, if we're talking about local max and min values, that's just the y values of the local max and min points. So there's a local max value at this y value of 3.3, and there's a local min value of 2, this point's y value. There are no absolute max or min values for this function. In this video, we defined absolute and local max and min points and values. This video is about symmetry of graphs and functions. We say that a graph is symmetric with respect to the x-axis if the graph has mirror symmetry with the x-axis as the mirror line. This graph here is an example. Here is the mirror line. Notice that the point 5, 3 is on this graph, and so its mirror image, 5, negative 3, is also on the graph. Similarly, the point 2, 2 is on the graph, and its mirror image, 2, negative 2, is on the graph. For any point x, y on a graph, its mirror image, when you flip over the x-axis, will have coordinates, the same x-coordinate, and the opposite of the y-coordinate. Therefore, we can say that a graph is symmetric with respect to the x-axis if whenever a point xy is on the graph, the point x, negative y is also on the graph. We say that a graph is symmetric with respect to the y-axis if it has mirror symmetry with the y-axis as the mirror line. This graph is symmetric with respect to the y-axis. Here is the mirror line. Notice that the point with coordinates 2, 3 is on this graph. Its mirror image, which is also on the graph, has coordinates negative 2, 3. So the same y-coordinate, but the opposite x-coordinate. And in fact, if I take any point with coordinates x, y, and I want its mirror image with the y-axis as a mirror line, I'm going to get a point with the same height, the same y-coordinate, but the opposite x-coordinate. So I can say that a graph is symmetric with respect to the y-axis if whenever a point xy is on the graph, the point negative x, y is also on the graph. Finally, a graph is symmetric with respect to the origin if it has 180-degree rotational symmetry around the origin. This means that if I spin it by 180 degrees, the graph should line up exactly with itself. Rotating a graph by 180 degrees is the same thing as turning it upside down. So one way to see if a graph has symmetry with respect to the origin is to turn it upside down and see if it looks exactly the same. This one does. Playing around with points, I notice that the point 1, negative 2 is on this graph. If I rotate that point around the origin by 180 degrees, I get to the point with coordinates negative 1, 2. If I start with the point on the graph with coordinates 2, 3, and I rotate by 180 degrees, I get the point with coordinates negative 2, negative 3. And in general, if I start with a point x, y, and I rotate that 180 degrees around the origin, I get the point with coordinates negative x, negative y. So we can say that a graph is symmetric with respect to the origin if whenever a point xy is on the graph, the point negative x, negative y is also on the graph. Please pause the video for a moment and decide which of these graphs are symmetric with respect to the x-axis, the y-axis, and the origin. Some graphs may have more than one type of symmetry. Graph A is symmetric with respect to the origin, because if you rotate it by 180 degrees, that is, you turn it upside down, it looks exactly the same. It does not have any mirror symmetry, so it's not symmetric with respect to the x-axis or the y-axis. Graph B does have mirror symmetry. I'll draw on the two mirror lines. So it's both symmetric with respect to the x-axis and symmetric with respect to the y-axis. It also looks exactly the same upside down, so it's also symmetric with respect to the origin. Graph C is symmetric with respect to the y-axis, but has no other symmetry. And graph D is symmetric with respect to the x-axis, with no other symmetry. We use the words even and odd to describe functions whose graphs have certain kinds of symmetry. A function is even if its graph is symmetric with respect to the y-axis. Remember that being symmetric with respect to the y-axis means that whenever a point xy is on the graph, its mirror image, negative xy, is also on the graph. That is, the y values corresponding to x and negative x are the same. Using function notation, I can write these points as the points with coordinates x, f of x, and negative x, f of negative x, since the y value for a function is given by f of its x value. So we can say that a function f of x is even if f of negative x equals f of x for all x values in its domain. The function has the same height at x and negative x. For example, we can see that the function f of x equals x squared plus 3 is even, and one way to see this is by looking at its graph, which looks pretty much like the graph I've drawn, and noticing that its graph is symmetric across the y-axis. But we can also check that this function is even algebraically without knowing anything about its graph. All we have to do is check that f of negative x is equal to f of x. So if we plug in negative x for x into this formula, that's negative x squared plus 3, but negative x squared is the same thing as x squared. And so this is exactly the same thing as f of x. And the property of being even is satisfied. We say that a function f of x is odd if its graph is symmetric with respect to the origin. Recall that a graph is symmetric with respect to the origin means that whenever a point xy is on the graph, its 180 degree rotated point, negative x, negative y, is also on the graph. That is, the graph's y value at x and the graph's y value at negative x are the opposites of each other. Same magnitude, but opposite sign. If we use function notation for the coordinates of these points, this one is x, f of x, and this one is negative x, f of negative x, right? Because the y value for a function at the x value of negative x is just f of negative x. So for a function to be odd, we see that f of negative x, that y value, has to be the opposite of f of x, the other guy's y value. A function f of x is odd if f of negative x is the negative of f of x for all x in its domain. Let's look at this example. We could draw its graph and verify the function's odd by seeing that rotational symmetry around the origin on its graph, but we can also figure it out algebraically by checking to see if f of negative x is equal to negative of f of x. So let's plug in negative x for x in the formula for f. That gives us 5 times negative x minus 1 over negative x. that simplifies to negative 5x plus 1 over x, and we can see that that is actually the negative of 5x minus 1 over x by factoring out a negative sign, which is negative f of x. So the property for being odd holds. In this video, we talked about symmetry with respect to the x-axis, symmetry with respect to the y-axis, and symmetry with respect to the origin. Functions that are symmetric with respect to the y-axis are even functions, and functions that are symmetric with respect to the origin are odd functions. There's no word for functions that are symmetric with respect to the x-axis, and that's because if your graph is symmetric with respect to the x-axis, it's not going to be a function. This video gives the graphs of some commonly used functions that I call the Toolkit functions. The first function is the function y equals x. Let's plot a few points on the graph of this function. If x is 0, y is 0. If x is 1, y is 1. And so on, y is always equal to x. It doesn't have to just be an integer, it can be any real number. And connecting the dots, we get a straight line through the origin. Let's look at the graph of y equals x squared. If x is 0, y is 0, so we go through the origin again. If x is 1, y is 1. And if x is negative 1, y is also 1. The x value of 2 gives a y value of 4, and the x value of negative 2 gives a y value of 4 also. Connecting the dots, we get a parabola. Notice this function is an even function. That means it has mirror symmetry across the y-axis. The left side looks exactly like the mirror image of the right side. That happens because when you square a positive number like 2, you get the exact same y value as when you square its mirror image x value of negative 2. The next function, y equals x cubed, I'll call that a cubic. Let's plot a few points. When x is 0, y is 0. When x is 1, y is 1. When x is negative 1, y is negative 1. 2 goes with the point 8 way up here, and an x value of negative 2 is going to give us negative 8. If I connect the dots, I get something that looks kind of like this. This function is what's called an odd function because it has 180-degree rotational symmetry around the origin. If I rotate this whole graph by 180 degrees, or in other words, turn the paper upside down, I'll get exactly the same shape. The reason this function has this odd symmetry is because when I cube a positive number and get its y value, and cube the corresponding negative number to get its y value, the negative number cubed gives us exactly the negative of the y value you would get with cubing the positive number. Let's look at the next example, y equals the square root of x. Notice that the domain of this function is just x values bigger than or equal to 0 because we can't take the square root of a negative number. Let's plug in a few x values. X is 0 gives y is 0. X is 1, square root of 1 is 1. Square root of 4 is 2. And connecting the dots, I get a function that looks like this. The absolute value function is next. Again, if we plug in a few points, x is 0 goes with y equals 0. X is 1 gives us 1. The absolute value of negative 1 is 1. 2 is on the graph, and the absolute value of negative 2 is 2. I'm ending up getting a V-shaped graph. It also has even or mirror symmetry. Y equals 2 to the x is what's known as an exponential function. That's because the variable x is in the exponent. If I plot a few points, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 to the minus 1 is 1/2. I'll plot these on my graph. Let me fill in a few more points. So let's see, 2 cubed is 8, that's way up here, and -2 gives me 1/4, 1/8. Connecting the dots, I get something that's shaped like this. You might have heard the expression exponential growth when talking about, for example, population growth. This function represents exponential growth. It grows very, very steeply. Every time we increase the x-coordinate by 1, we double the y-coordinate. We could also look at a function like y equals 3 to the x, or sometimes y equals e to the x, where e is just a number about 2.7. These functions look very similar. It's just the bigger base makes us rise a little more steeply. Now let's look at the function y equals 1 over x. It's not defined when x is 0, but I can plug in x equals 1/2. 1 over 1/2 is 2. 1 over 1 is 1, and 1 over 2 is 1/2. If I connect the dots, I get this shape in the first quadrant, but I haven't looked at negative values of x. When x is negative, 1 over -1 is -1. 1 over -1/2 is -2, and I get a similar looking piece in the third quadrant. This is an example of a hyperbola, and it's also an odd function because it has that 180-degree rotational symmetry. If I turn the page upside down, it'll look exactly the same. Finally, let's look at y equals 1 over x squared. Again, it's not defined when x is 0, but I can plug in points like 1/2 for x. Let's see, 1 over 1/2 squared is 1 over 1/4, which is 4. And 1 over 1 squared, 1 over 2 squared is 1/4. It looks pretty much like the previous function. It's just a little bit more extreme, rises a little more steeply, falls a little more dramatically. But for negative values of x, something a little bit different goes on. For example, 1 over -2 squared is just 1 over 4, which is 1/4. So I can plot that point there. And 1 over -1 squared, that's just 1. So my curve for negative values of x is going to lie in the second quadrant, not the third quadrant. This is an example of an even function because it has perfect mirror symmetry across the y-axis. These are the toolkit functions, and I recommend you memorize the shape of each of them. That way you can draw at least a rough sketch very quickly without having to plug in points. That's all for the graphs of the toolkit functions. If we change the equation of a function, then the graph of the function changes or transforms in predictable ways. This video gives some rules and examples for transformations of functions. To get the most out of this video, it's helpful if you're already familiar with the graph of some typical functions. I call them toolkit functions, like y equals square root of x, y equals x squared, y equals the absolute value of x, and so on. If you're not familiar with those graphs, I encourage you to watch my video called Toolkit Functions first before watching this one. I want to start by reviewing function notation. If g of x represents the function the square root of x, then we can rewrite these expressions in terms of square roots. For example, g of x minus 2 is the same thing as the square root of x minus 2. G of quantity x minus 2 means we plug in x minus 2 everywhere we see an x. So that would be the same thing as the square root of quantity x minus 2. In this second example, I say that we're subtracting 2 on the inside of the function, because we're subtracting 2 before we apply the square root function. Whereas on the first example, I say that the minus 2 is on the outside of the function. We're doing the square root function first and then subtracting 2. In this third example, g of 3x, we're multiplying by 3 on the inside of the function. To evaluate this in terms of square root, we plug in the entire 3x for x in the square root function. That gives us the square root of 3x. In the next example, we're multiplying by 3 on the outside of the function. This is just 3 times the square root of x. Finally, g of minus x means the square root of minus x. This might look a little odd because we're not used to taking the square root of a negative number, but remember that if x itself is negative, like negative 2, then negative x will be negative negative 2 or positive 2, so we'll really be taking the square root of a positive number in that case. Let me record which of these are inside and which of these are outside of my function. In this next set of examples, we're using the same function, g of x is square root of x, but this time we're starting with an expression with square roots in it and trying to write it in terms of g of x. So the first example, the plus 17 is on the outside of my function because I'm taking the square root of x first and then adding 17. So I can write this as g of x plus 17. In the second example, I'm taking x and adding 12 first, then I take the square root of the whole thing. Since I'm adding the 12 to x first, that's on the inside of my function. So I write that as g of the quantity x plus 12. Remember that this notation means I plug in the entire x plus 12 into the square root sign, which gives me exactly square root of x plus 12. In this next example, I'm doing the square root first and then multiplying by negative 36. So my minus 36 multiplication is outside my function. I can rewrite this as minus 36 times g of x. Finally, in this last example, I take x, multiply by a fourth, and then apply the square root of x. So that's the same thing as g of 1/4 x. My 1/4 x is on the inside of my function. In other words, it's inside the parentheses when I use function notation. Let's graph the square root of x and two transformations of this function. Y equals the square root of x goes through the points 0, 0, 1, 1, and 4, 2, since the square root of 4 is 2, and looks something like this. In order to graph y equals the square root of x minus 2, notice that the minus 2 is on the outside of the function. That means we're going to take the square root of x first and then subtract 2. So for example, if we start with the x value of 0 and compute the square root of 0, that's 0, then we subtract 2 to give us a y value of negative 2. An x value of 1, which under the square root function had a y value of 1, now has a y value that's decreased by 2. 1 minus 2 is negative 1. And finally, an x value of 4, which under the square root function had a y value of 2, now has a y value of 2 minus 2, or 0. Its y value is also decreased by 2. If I plot these new points, 0 goes with negative 2, 1 goes with negative 1, and 4 goes with 0, I have my transformed graph. Because I subtracted 2 on the outside of my function, my y values were decreased by 2, which brought my graph down by 2 units. Next, let's look at y equals the square root of quantity x minus 2. Now we're subtracting 2 on the inside of our function, which means we subtract 2 from x first and then take the square root. In order to get the same y value of 0 as we had in our blue graph, we need our x minus 2 to be 0, so we need our original x to be 2. In order to get the y value of 1 that we had in our blue graph, we need to be taking the square root of 1. So we need x minus 2 to be 1, which means that we need to start with an x value of 3. And in order to reproduce our y value of 2 from our original graph, we need the square root of x minus 2 to be 2, which means we need to start out by taking the square root of 4, which means our x minus 2 is 4, so our x should be up there at 6. If I plot my x values with my corresponding y values of square root of x minus 2, I get the following graph. Notice that the graph has moved horizontally to the right by 2 units. To me, moving down by 2 units makes sense because we're subtracting 2, so we're decreasing y's by 2 units. But the minus 2 on the inside, that kind of does the opposite of what I expect. I might expect it to move the graph left. I might expect the x values to be going down by 2 units, but instead it moves the graph to the right, because the x units have to go up by 2 units in order to get the right square root when I then subtract 2 units again. The observations we made for these transformations of functions hold in general according to the following rules. First of all, numbers on the outside of the function, like in our example y equals the square root of x minus 2, those numbers affect the y values and result in vertical motions, like we saw. These motions are in the direction you expect, so subtracting 2 moves us down by 2. If we were adding 2 instead, that would move us up by 2. Numbers on the inside of the function, that's like our example y equals the square root of quantity x minus 2, those affect the x values and result in a horizontal motion. These motions go in the opposite direction from what you expect. Remember, the minus 2 on the inside actually shifted our graph to the right. If it had had a plus 2 on the inside, that would actually shift our graph to the left. Adding results in a shift, those are called translations, but multiplying, like something like y equals 3 times the square root of x, that would result in a stretch or shrink. In other words, if I start with the square root of x and then want to graph y equals 3 times the square root of x, that stretches my graph vertically by a factor of 3. Like this. If I want to graph y equals 1/3 times the square root of x, that shrinks my graph vertically by a factor of 1/3. Finally, a negative sign results in reflection. For example, if I start with a graph of y equals the square root of x, and then want to graph y equals the square root of negative x, that's going to do a reflection in the horizontal direction because the negative is on the inside of the square root sign. A reflection in the horizontal direction means a reflection across the y-axis. If instead I want to graph y equals negative the square root of x, that negative sign on the outside means a vertical reflection, a reflection across the x-axis. Pause the video for a moment and see if you can describe what happens in these 4 transformations. In the first example, we're subtracting 4 on the outside of the function. Adding and subtracting means a translation or shift, and since we're on the outside of the function, it affects the y value, so that's moving us vertically. So this transformation should take the square root of graph and move it down by 4 units. That would look something like this. In the next example, we're adding 12 on the inside. That's still a translation, but now we're moving horizontally, and so since we go the opposite direction we expect, we are going to go to the left by 12 units. That's going to look something like this. In the next example, we're multiplying by 3 and introducing a negative sign, both on the outside of our function. Outside our function means we're affecting the y values. And multiplication means we're stretching by a factor of 3. The negative sign means we reflect in the vertical direction. Here's stretching by a factor of 3 vertically before I apply the minus sign, and now the minus sign reflects in the vertical direction. Finally, in this last example, we're multiplying by 1/4 on the inside of our function. We know that multiplication means stretch or shrink, and since we're on the inside, it's a horizontal motion, and it does the opposite of what we expect. So instead of shrinking by a factor of 1/4 horizontally, it's actually going to stretch by the reciprocal, a factor of 4 horizontally. That'll look something like this. Notice that stretching horizontally by a factor of 4 looks kind of like shrinking vertically by a factor of 1/2. And that's actually borne out by the algebra, because the square root of 1/4 x is the same thing as the square root of 1/4 times the square root of x, which is the same thing as 1/2 times the square root of x. And so now we can see algebraically that a vertical shrink by a factor of 1/2 is the same as a horizontal stretch by a factor of 4, at least for this function, the square root function. This video gave some rules for transformations of functions, which I'll repeat below. Numbers on the outside correspond to changes in the y values, or vertical motions. Numbers on the inside of the function affect the x values and result in horizontal motions. Adding and subtracting corresponds to translations, or shifts. Multiplying and dividing by numbers corresponds to stretches and shrinks. and putting in a negative sign corresponds to a reflection. A horizontal reflection if the negative sign is on the inside, and a vertical reflection if the negative sign is on the outside. Knowing these basic rules about transformations empowers you to be able to sketch graphs of much more complicated functions, like y equals 3 times the square root of x plus 2, by simply considering the transformations one at a time. This video introduces piecewise functions. A piecewise function is a function who's defined in pieces by 2 or more different rules that apply for different x values. The rule for calculating this function is you calculate negative x squared if x is less than 1, but you calculate negative 2x plus 3 if x is greater than or equal to 1. So if we want to find f of negative 2, well, negative 2 is less than 1, so the first rule applies. And we compute f of negative 2 by plugging in negative 2 for x in the first rule, so that's negative 4. Next, if we want to find f of 1, well, 1 is right on the border in between the 2 rules, but because we have a greater than or equal to here, when x is equal to 1, we apply this rule. And so we can plug 1 into the formula negative 2x plus 3, so that's negative 2 times 1 plus 3, which gives us 1 as our output. Finally, if we want to compute f of 3, since 3 is bigger than or equal to 1, the second rule applies, and we plug 3 into that rule. That gives us an answer of negative 3. To graph f, it makes sense to also draw the graph in pieces. First, I'm going to draw the graph of minus x squared. Just x squared would be a parabola opening up, so minus x squared is a parabola opening down, goes through the points negative 1, negative 1, and 1, negative 1. So it looks something like this. Now I've drawn the whole parabola, but the rule actually only applies when x is less than 1. So I'll keep the part of the parabola when x is less than 1, and I'll erase the part of the parabola when x is greater than or equal to 1. I'll leave an open circle here when x equals 1, since that point is not included in this definition either. Next, I'm going to draw the second piece, the line y equals minus 2x plus 3. So that's a line with slope negative 2 and intercept, y-intercept 3. So it goes through this point 0, 3, and then it goes over by 1 and down by 2. So it goes through the point 1, 1, over by 1, down by 2, and I can continue and draw this straight line. Again, we only want part of this graph, the part where x is greater than or equal to 1, so I'll erase the part where x is less than 1, this part here. This time I'm going to leave a closed circle where x is equal to 1, since that point is included on that graph. When drawing this graph, it's good to think about what happens when x equals 1, the border point, both in the second rule, where we actually include that point, and in the first rule, where we don't actually include that point, but we kind of have to draw it in order to, anyway, to draw the open circle here. Now the last question asks us if this function is continuous. The informal definition of continuity that I'm going to use is that a function is continuous if you can draw the whole thing without picking up your pencil. And in this case, we can't, because we have to pick up our pencil to get from the jump here up to here. So this function is not continuous. It's got a discontinuity when x is 1, which is exactly the border point between the 2 rules. Often, piecewise functions will have discontinuities where they transition from one rule to the next. However, it's possible to have a piecewise defined function that has no discontinuity if the 2 pieces happen to line up perfectly. For example, if we change the function's definition slightly, I'll call it g of x this time, to still be the negative x squared when x is less than 1, but this time negative 2x plus 1 if x is bigger than or equal to 1. Then when we graph it, the parabola piece will look the same, but the linear piece will be 2 units lower than before, and so it'll actually start right here at 1, negative 1 and go down, and our function will be continuous. That's all for this introduction to piecewise functions. The inverse of a function undoes what the function does. So the inverse of tying your shoes would be to untie them. And the inverse of the function that adds 2 to a number would be the function that subtracts 2 from a number. This video introduces inverses and their properties. Suppose f of x is the function defined by this chart. In other words, f of 2 is 3, f of 3 is 5, f of 4 is 6, and f of 5 is 1. The inverse function for f, written f superscript -1 x, undoes what f does. Since f takes 2 to 3, f inverse takes 3 back to 2. So we write this, f superscript -1 of 3 is 2. Similarly, since f takes 3 to 5, f inverse takes 5 to 3. And since f takes 4 to 6, f inverse of 6 is 4. And since f takes 5 to 1, f inverse of 1 is 5. I'll use these numbers to fill in the chart. Notice that the chart of values when y equals f of x and the chart of values when y equals f inverse of x are closely related. They share the same numbers, but the x values for f of x correspond to the y values for f inverse of x, and the y values for f of x correspond to the x values for f inverse of x. That leads us to the first key fact. Inverse functions reverse the roles of y and x. I'm going to plot the points for y equals f of x in blue. Next, I'll plot the points for y equals f inverse of x in red. Pause the video for a moment and see what kind of symmetry you observe in this graph. How are the blue points related to the red points? You might have noticed that the blue points and the red points are mirror images. Over the mirror line, y equals x. So our second key fact is that the graph of y equals f inverse of x can be obtained from the graph of y equals f of x by reflecting over the line y equals x. This makes sense because inverses reverse the roles of y and x. In this same example, let's compute f inverse of f of 2. This open circle means composition. In other words, we're computing f inverse of f of 2. We compute this from the inside out, so that's f inverse of 3, since f of 2 is 3, and f inverse of 3 we see as 2. Similarly, we can compute f of f inverse of 3, and that means we take f of f inverse of 3. Since f inverse of 3 is 2, that's the same thing as computing f of 2, which is 3. Please pause the video for a moment and compute these other compositions. You should have found that in every case, if you take f inverse of f of a number, you get back to the very same number you started with. And similarly, if you take f of f inverse of any number, you get back to the same number you started with. So in general, f inverse of f of x is equal to x, and f of f inverse of x is also equal to x. This is the mathematical way of saying that f and f inverse undo each other. Let's look at a different example. Suppose that f of x is x cubed. Pause the video for a moment and guess what the inverse of f should be. Remember, f inverse undoes the work that f does. You might have guessed that f inverse of x is going to be the cube root function. And we can check that this is true by looking at f of f inverse of x. That's f of the cube root of function, which means the cube root function cubed, which gets us back to x. Similarly, if we compute f inverse of f of x, that's the cube root of x cubed, and we get back to x again. So the cube root function really is the inverse of the cubing function when we compose the two functions we get back to the number that we started with. It'd be nice to have a more systematic way of finding inverses of functions besides guessing and checking. One method uses the fact that inverses reverse the roles of y and x. So if we want to find the inverse of the function f of x equals 5 minus x over 3x, we can write it as y equals 5 minus x over 3x, reverse the roles of y and x to get x equals 5 minus y over 3y, and then solve for y. To solve for y, let's multiply both sides by 3y, bring all terms with y's in them to the left side, and all terms without y's in them to the right side, factor out the y, and divide to isolate y. This gives us f inverse of x as 5 over 3x plus 1. Notice that our original function, f, and our inverse function, f inverse, are both rational functions, but they're not the reciprocals of each other. And in general, f inverse of x is not usually equal to 1 over f of x. This can be confusing because when we write 2 to the minus 1, that does mean 1 over 2, but f to the minus 1 of x means the inverse function and not the reciprocal. It's natural to ask if all functions have inverse functions. That is, for any function you might encounter, is there always a function that is its inverse? In fact, the answer is no. See if you can come up with an example of a function that does not have an inverse function. The word function here is key. Remember that a function is a relationship between x values and y values such that for each x value in the domain, there's only one corresponding y value. One example of a function that does not have an inverse function is the function f of x equals x squared. To see that the inverse of this function is not a function, note that for the x squared function, the number 2 and the number negative 2 both go to the number 4. So if I had an inverse, it would have to send 4 to both 2 and negative 2. The inverse would not be a function. It might be easier to understand the problem when you look at a graph of y equals x squared. Recall that inverse functions reverse the roles of y and x and flip the graph over the line y equals x. But when I flip the green graph over the line y equals x, I get this red graph. This red graph is not the graph of a function because it violates the vertical line test. The reason it violates the vertical line test is because the original green function violates the horizontal line test and has two x values with the same y value. In general, a function f has an inverse function if and only if the graph of f satisfies the horizontal line test, i.e. every horizontal line intersects the graph in at most one point. Pause the video for a moment and see which of these four graphs satisfy the horizontal line test. In other words, which of the four corresponding functions would have an inverse function. You may have found that graphs A and B violate the horizontal line test, so their functions would not have inverse functions. But graphs C and D satisfy the horizontal line test, so these graphs represent functions that do have inverses. Functions that satisfy the horizontal line test are sometimes called one-to-one functions. Equivalently, a function is one-to-one if for any two different x values, x1 and x2, the y values f of x1 and f of x2 are different numbers. Sometimes this is said f is one-to-one if whenever f of x1 is equal to f of x2, then x1 has to equal x2. As our last example, Let's try to find p inverse of x, where p of x is the square root of x minus 2, drawn here. If we graph p inverse on the same axis as p of x, we get the following graph, simply by flipping over the line y equals x. If we try to solve the problem algebraically, we can write y equal to square root of x minus 2, reverse the roles of y and x, and solve for y by squaring both sides and adding 2. Now if we were to graph y equals x squared plus 2, that would look like a parabola. It would look like the red graph we've already drawn together with another arm on the left side. But we know that our actual inverse function consists only of this right arm. We can specify this algebraically by making the restriction that x has to be bigger than or equal to 0. This corresponds to the fact that on the original graph for the square root of x, y was only greater than or equal to 0. Looking more closely at the domain and range of p and p inverse, we know that the domain of p is all values of x such that x minus 2 is greater than or equal to 0, since we can't take the square root of a negative number. This corresponds to x values being greater than or equal to 2, or in interval notation, the interval from 2 to infinity. The range of p, we can see from the graph, is all y values greater than or equal to 0, or the interval from 0 to infinity. Similarly, based on the graph, we see the domain of p inverse is x values greater than or equal to 0, the interval from 0 to infinity, and the range of p inverse is y values greater than or equal to 2, or the interval from 2 to infinity. If you look closely at these domains and ranges, you'll notice that the domain of p corresponds exactly to the range of p inverse, and the range of p corresponds to the domain of p inverse. This makes sense because inverse functions reverse the roles of y and x. The domain of f inverse of x is the x values for f inverse, which corresponds to the y values, or the range of f. The range of f inverse is the y values for f inverse, which correspond to the x values, or the domain of f. In this video, we discussed 5 key properties of inverse functions. Inverse functions reverse the roles of y and x. The graph of y equals f inverse of x is the graph of y equals f of x reflected over the line y equals x. When we compose f with f inverse, we get the identity function y equals x, and similarly, when we compose f inverse with f, that brings x to x. In other words, f and f inverse undo each other. The function f of x has an inverse function if and only if the graph of y equals f of x satisfies the horizontal line test. And finally, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. These properties of inverse functions will be important when we study exponential functions and their inverses, logarithmic functions. There are different ways of describing the size of an angle. This video explains how to convert between them. Angles are commonly measured using either degrees or radians. If we're talking about degrees, then a full circle, by convention, is 360 degrees. A half circle, then, would be 180 degrees, and if I wanted to do, say, a third of a circle, that would be a third of 360 degrees, or 120 degrees. If we're using radians instead, then going all the way around the circle is called 2 pi radians. The 2 pi was chosen because that's the circumference of a circle with a radius of 1. A half circle is then half of 2 pi radians, which is pi radians. And if I wanted to do, say, a quarter of a circle, that would be a quarter of my 2 pi radians. A quarter of 2 pi is pi over 2. To convert between degrees and radians, it's handy to use the fact that 180 degrees corresponds to pi radians. Both of these represent half of a circle. Let's convert negative 135 degrees to radians. Now you might be wondering, what does a negative angle even mean? Well, by convention, if we go in the counterclockwise direction, that's considered a positive angle. And if we go in the clockwise direction, that's considered a negative angle. To convert negative 135 degrees to radians, I could multiply by pi radians per 180 degrees. Notice that the degrees cancel here, and I end up with negative 135 pi over 180 radians. That simplifies to negative 3 pi over 4 radians, or if I convert pi to a decimal, that's negative 2.3562 radians up to 4 decimal places. But usually if the answer is a simple fraction times pi, it's better to leave it in that form rather than convert it to a decimal. I can also go the other direction and convert radians to degrees. 5 pi over 4 radians. Now again, I need to use the fact that pi radians is 180 degrees, but if I write it like this, with radians on the top and degrees on the bottom, then the radians won't cancel. So that doesn't work. Instead, I need to multiply by the reciprocal 180 degrees over pi radians so that I can cancel the radians and be left with degrees. Cancel, and I get 5 pi times 180 over 4 pi degrees. Now the pi's also cancel, and this simplifies to 225 degrees. Converting 7 radians to degrees is similar. I need to multiply by 180 degrees over pi radians. If I work out 7 times 180 over pi on my calculator, I get 401.07 degrees up to 2 decimal places. Notice that my answer, a little more than 400, is more than 360 degrees, so this is more than a full circle. That makes sense, since 7 radians is more than 2 pi radians, since pi is itself a little more than 3. Sometimes angles are given in terms of degrees, minutes, and seconds, as in 32 degrees, 17 minutes, and 25 seconds. A minute is defined as 1/60th of a degree. A second is defined as 1/60th of a minute. But since a minute is itself 1/60th of a degree, this is 1/60th of 1/60th of a degree, or 1 over 3600 of a degree. You can also think of this by saying that there are 60 minutes in 1 degree, and there are 3,600 seconds in 1 degree. Let's convert this number of degrees, minutes, and seconds to a decimal number of degrees. We know that we have 32 degrees plus 17 minutes plus 25 seconds. I'm going to copy down the 32 degrees, but I need to convert the minutes to degrees. I know that there's 60 minutes in 1 degree. If I want the units to cancel, I better put the degrees on the top. So 1 degree corresponds to 60 minutes. Similarly, if I want to convert seconds to degrees, 25 seconds, I know that there are 3,600 seconds in 1 degree. I want the degrees to end up on the top, and I want the seconds on the bottom to cancel with the 25 seconds, so I need to write it this way. Okay, now I can write this as 32 degrees plus 17 over 60 degrees plus 25 over 3,600 degrees, and because the minutes canceled and the seconds canceled. If I add this all up on my calculator, I get 32.2903 degrees up to 4 decimal places. I can also go the other direction and convert a decimal number of degrees into degrees, minutes, and seconds. I'm starting out with 247 degrees plus a decimal number of degrees left over. If I want to convert 0.3486 degrees to minutes, well, I know that I have 60 minutes in 1 degree. This time I want the minutes on the top and the degrees on the bottom so that my degrees will cancel. So I just multiply my decimal by 60 and I end up with 20.916 minutes. Let me copy this down. And now I'm going to take the 0.916 minutes and convert those to seconds. So I know that there are 60 seconds in 1 minute. So canceling my units again, I just multiply by 60, which gives me 54.96 minutes. I can copy this down as is, or I can round off my seconds and get 247 degrees, 20 minutes, and 55 seconds. Converting between different ways of measuring angles is all about unit conversion. To convert between radians and degrees, we use the fact that pi radians corresponds to 180 degrees. To convert between minutes and seconds and degrees, we use the fact that 60 minutes corresponds to 1 degree and 60 seconds corresponds to 1 minute. If you have a circle, a piece of the circumference is called an arc, and a wedge of pi for that circle is called a sector. This video explains how to calculate the length of the arc and the area of the sector in terms of the angle and the radius of the circle. The circumference of a circle is given by the formula the circumference equals 2 pi times the radius. Let's use that to solve the following problem. A circular pool has a radius of 8 meters. Find the arc length spanned by a central angle of 2.5 radians. So this angle from the center of the circle is supposed to be 2.5 radians. I've drawn the angle as a little bit less than half the circle because half the circle would be pi radians, which is 3.141 radians. So I want to find the length of this arc. I know that the total circumference is going to be 2 pi times 8 meters. But I just want a fraction of the circumference. The arc length I want is going to be given by the fraction of the circle that the angle makes times the circumference of the circle. The fraction of the circle that I want is given by the ratio of 2.5 radians over the total number of radians in the circle, which is 2 pi radians. Multiply that by the circumference, which we said was 2 pi times 8 meters. Notice that the 2 pi's cancel, and I'm left with just 2.5 times 8 meters, which is 10 meters. In general, the arc length is related to the angle it spans by considering the arc length to be the fraction of the circle you get by taking the angle over the total angle of the circle of 2 pi times the circumference, which is 2 pi r. Since the 2 pi's cancel, as they did in our example, that means that arc length is given by theta times r. Here r is the radius of the circle and theta is the angle. It's important to note that theta needs to be measured in radians, not degrees, for this to work. That's because when I took this ratio, I was using 2 pi radians for the total measure of the circle, so it's important that theta also be in radians. The area of a circle is given by the formula pi r squared, where r is the radius. Let's use that fact to find the area of the sector of a circle of radius 10 meters that spans an angle of pi over 6 radians. We know that the total area of the circle is given by pi times 10 meters squared, or 100 pi meters squared. But we just want a fraction of that area to give us the area of our sector. So we want to take the fraction of the circle that the sector makes times the area of the circle. Well, the fraction of the circle is given by the angle of pi over 6 over the total angle in the whole circle of 2 pi, and we'll times that by the 100 pi meters squared. That simplifies to 100 pi over 12 meters squared, or 25/3 pi meters squared. As a decimal, that's 26.18 meters squared up to 2 decimal places. In general, if you want to find the area of a sector, you can take the fraction of the circle that the sector spans out times the area of the circle, pi r squared. Notice that the fraction of the circle is given by the angle that the sector makes in radians divided by the 2 pi radians in the circle. Since the pi's cancel, we can simplify this formula by saying the area is given by theta over 2 times r squared, where theta is the angle of the sector in radians. Again, it's important that this angle be in radians, since that's how we're doing our fraction of our circle comparison. As usual, r represents the radius of the circle. Notice that if you don't have your angle in radians, if it's in degrees instead, not a big deal, because we can always convert from degrees to radians first before using our formula. In this video, we saw that for a sector of angle theta given in radians, the arc length is given by the formula theta times r, and the area of the sector is given by theta over 2 times r squared, where r is the radius of the circle. This video defines linear and radial speed for a rotating circle and explains how to convert between them. Consider a spinning wheel. The angular speed is the angle it goes through in a unit of time. I can write that as angle per time. The units will be something like radians per second, if the angle's measured in radians and the time's measured in seconds. Or I guess we could do degrees per minute, etc. The linear speed is the speed of a point on the rim of the wheel. So that is the distance a point on the rim of the wheel travels in a unit of time. I can think of that as distance per time, and so it has units of something like meters per second, for example, or it could be feet per minute, etc. Suppose we have a Ferris wheel with radius 20 meters that's making 1 revolution every 2 minutes. We want to find its angular speed and the linear speed of a point on its rim. Now the Ferris wheel is going 1 revolution every 2 minutes. So that's 1/2 revolution per minute. I want to find the angular speed, which is the angle it goes through in a unit of time. I've already got a unit of time in the denominator, minutes, but I've got to somehow convert revolutions to angle. So my angular speed, 1/2 revolutions per minute. 1 revolution, I'll put that on the bottom so the units will cancel out. 1 revolution is going through an angle of 2 pi radians. That means my angular speed is going to be 1/2 times 2 pi radians per minute, or pi radians per minute. The linear speed, the speed of a point on the rim, well, the wheel is going pi radians per minute. I got to somehow convert radians into distance. So I know that when I go 2 pi radians, so that's all the way around the circle, I'm going all the way around the circumference in distance. So that would be 2 pi times the radius, or 2 pi times 20 meters. The 2 pi's cancel, as do the radians, and I'm left with 20 pi meters per minute. Let's review how we got from angular speed to linear speed in order to get a more general formula. I'll call the angular speed omega, it looks like a W, and I'll call the linear speed V. In the previous problem, we found the linear speed V by starting with the angular speed omega and multiplying it by the circumference divided by 2 pi. That's because the point on the rim travels the whole circumference as it goes through an angle of 2 pi all the way around a circle. So I'll write that down here, circumference over 2 pi. But since I know that my circumference is given by the formula 2 pi r, and the 2 pi's cancel, as they did in the previous problem, that shows that the linear speed is the angular speed times r, where r is the radius of the circle. In this video, we defined linear speed and radial speed and found that linear speed was radial speed times the radius of the circle. This video introduces the trig functions sine, cosine, tangent, secant, cosecant, and cotangent for right triangles. For a right triangle with sides of length A, B, and C and an angle theta as drawn, we define sine of theta as the length of the opposite side over the hypotenuse. The side that's opposite to our angle theta has measure A, and the hypotenuse is this side here with measure C, so that would be A over C for this triangle. Cosine of theta is defined as the length of the adjacent side over the length of the hypotenuse. This side here is the side adjacent to theta. Of course, the hypotenuse is also adjacent to theta, but it's special as the hypotenuse, so we don't think of it as the adjacent side. So that would be B over C. Tangent of theta is the opposite side length over the adjacent side length. So that would be A over B. The mnemonic to remember this is SOHCAHTOA. That's sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. In fact, there's a relationship between tangent and sine and cosine. Namely, tangent of theta is equal to sine of theta over cosine of theta. If you want to see why, that's because sine of theta over cosine of theta is given by sine, which is opposite over hypotenuse, divided by cosine, which is adjacent over hypotenuse. If we compute these fractions by flipping and multiplying, the hypotenuse length cancels, and we just get opposite over adjacent, which is by definition tangent of theta. There are three more trig functions that are defined in terms of sine, cosine, and tangent. First of all, there's secant of theta. By definition, that's 1 over cosine of theta. So it's going to be 1 over the adjacent over the hypotenuse, which is the hypotenuse over the adjacent, which in this triangle is C over B. Cosecant of theta is defined as 1 over sine theta. So that's 1 over the opposite over the hypotenuse, which is the hypotenuse over the opposite, and for this triangle, that's going to be C over A. Finally, cotangent of theta is defined as 1 over tan theta. So that's going to be 1 over opposite over adjacent. Flip and multiply, I get adjacent over opposite, which in this case is B over A. So notice that the values for cotangent, cosecant, and secant are the reciprocals of the values for tangent, sine, and cosine, respectively. Let's use these definitions to find the exact values of all 6 trig functions for the angle theta in this triangle. I'll start with sine of theta, that's opposite over hypotenuse. Well, for this angle theta, the opposite side is down here and has measure 2. The hypotenuse has measure 5. So sine theta is 2 over 5. Cosine theta is adjacent over hypotenuse, but I don't know the value of this side length. But fortunately, I can find it using the Pythagorean theorem. Since I have a right triangle here, I know that a squared, I'll call this side length a, plus b squared, where b is this other leg of the triangle, is equal to c squared, where c is the hypotenuse. So here I have a squared plus 2 squared equals 5 squared, which means that a squared plus 4 equals 25. A squared is 21, so a is plus or minus the square root of 21. But since I'm talking about the length of a side of a triangle, I can just use the positive answer. Returning to my computation of cosine theta, I can write it as adjacent, which is the square root of 21, over hypotenuse, which is 5. Tangent theta is the opposite over the adjacent, so that's going to be 2 over the square root of 21. To compute secant of theta, that's 1 over cosine theta, so that's going to be 1 over square root of 21 over 5, which is 5 over the square root of 21, the reciprocal of my cosine value. Cosecant theta is 1 over sine theta. That's going to be the reciprocal of my sine, so 5 halves. And cotangent theta is 1 over tan theta, so it's going to be the reciprocal of my tan value, square root of 21 over 2. Finally, we'll do an application. So if we have a kite that's flying at an angle of elevation, that's the angle from the horizontal, of 75 degrees, with a kite length string of 100 meters, we want to find out how high it is. I'll call the height y. Well, we want to relate the known quantities, this angle and this hypotenuse, to the unknown quantity. The unknown quantity is the opposite side of our triangle. So if we use sine of theta equals opposite over hypotenuse, then we can relate these known amounts, sine of 75 degrees, to our unknown amount, y, which is the opposite, and our known amount of 100 meters. Solving for y, this gives that y is 100 meters times sine of 75 degrees. We can use a calculator to compute sine of 75 degrees. Be sure you use degree mode and not radian mode when you type in the 75. When I do the computation, I get a final answer of 96.59 meters up to 2 decimal places. Notice that we're ignoring the height of the person in this problem. To remember the definitions of the trig functions, you can use the mnemonic SOHCAHTOA and the fact that secant is the reciprocal of cosine, cosecant the reciprocal of sine, and cotangent the reciprocal of tangent. In this video, I'll use geometry to compute the sine and cosine of a 30-degree angle, a 45-degree angle, and a 60-degree angle. One way to compute the sine of a 45-degree angle is to use a right triangle with a 45-degree angle. This particular right triangle has a hypotenuse of length 1. Since all the angles of the triangle have to add up to 180 degrees, and we already have 90 degrees and 45 degrees, the remaining angle must also be 45 degrees, so we have an isosceles triangle with two sides the same length. I'll call that side length A. If we want sine of 45 degrees, let's use this 45-degree angle here, then sine is opposite over hypotenuse. So if I can figure out how long this side length is, I'll be able to compute sine of 45 degrees. Now the Pythagorean theorem says this side length squared plus that side length squared equals the hypotenuse squared. So we have that a squared plus a squared equals 1 squared. I'll write that as 2a squared equals 1. So a squared is 1/2, and a is plus or minus the square root of 1/2. Since we're talking about the lengths of sides of triangles, I can just use the positive square root. It's customary to rewrite this as the square root of 1 over the square root of 2, which is 1 over the square root of 2, and then rationalize the denominator by multiplying the top and the bottom by the square root of 2. That gives me a square root of 2 in the numerator, and the square root of 2 squared in the denominator, which is the square root of 2 over 2. So these side lengths are the square root of 2 over 2. Now I can figure out the sine of 45 degrees by computing the opposite over the hypotenuse. I'm looking at this angle, so opposite is square root of 2 over 2, hypotenuse is 1. So the sine of 45 degrees is the square root of 2 over 2. Cosine of 45 degrees is adjacent over hypotenuse. That's this side length over this hypotenuse. So that's the square root of 2 over 1 again. What would happen if instead of using this triangle with hypotenuse 1, we use this triangle, also a 45, 45, 90 triangle, but with hypotenuse 5, not quite drawn to scale? Please pause the video for a moment and repeat the computation with this triangle. This time I'll call the side lengths b. Pythagorean theorem tells me b squared plus b squared equals 5 squared, so 2b squared equals 25, and b squared equals 25 over 2. b is going to be the plus or minus the square root of 25 over 2. Again, I can just use the positive version. And so b is the square root of 25 over the square root of 2, which is 5 over the square root of 2. Rationalizing the denominator, I get 5 root 2 over 2. Now sine of my 45-degree angle is opposite over hypotenuse, which is 5 square root of 2 over 2 divided by 5. That simplifies to the square root of 2 over 2 as before. And a similar computation shows that cosine of 45 degrees is also square root of 2 over 2 as before. This makes sense because sine and cosine are based on ratios of sides. And since these two triangles are similar triangles, they'll have the same ratios of sides. To find the sine and cosine of 30 degrees, let's use this 30, 60, 90 right triangle with hypotenuse 1. If we double the triangle, we get an angle of 30 here, so a total angle of 60 degrees here, and this angle is also 60 degrees. So we have a 60, 60, 60 triangle that's an equilateral triangle. All side lengths are the same. Since this side length has length 1, this side length is also 1, This entire side length is 1, which means the short side of our original triangle has length 1/2. Going back to my original triangle, let's use the Pythagorean theorem to find the length of its longer side, x. Pythagorean theorem says x squared plus 1/2 squared equals 1 squared. So x squared plus 1/4 equals 1. X squared is 3/4, and so x is plus or minus the square root of 3/4. Use the positive version and get the square root of 3 over the square root of 4, which is the square root of 3 over 2. Now, using our original triangle again, let's compute the sine of this 30-degree angle here. We know that sine of 30 degrees is opposite over hypotenuse. The opposite of this angle is 1/2, and the hypotenuse is 1. So we get a sine of 1/2 over 1, which is 1/2. Cosine of 30 degrees is adjacent over hypotenuse. So that's the square root of 3 over 2 divided by 1. To find sine of 60 degrees and cosine of 60 degrees, we can actually use this same green triangle and just focus on this upper corner angle of 60 degrees instead. So sine of 60 degrees, opposite over hypotenuse, but this time the opposite to this angle is the square root of 3 over 2. Cosine of 60 degrees, adjacent over hypotenuse, gives us 1/2. I'll summarize the results in this table below. Notice that a 30-degree angle corresponds to pi over 6 radians, since 30 degrees times pi over 180 is pi over 6. Similarly, 45 degrees corresponds to pi over 4 radians, and 60 degrees corresponds to pi over 3 radians. I recommend that you memorize the three numbers 1/2, root 2 over 2, and root 3 over 2, and the fact that 1/2 and root 3 over 2 go together, and root 2 over 2 goes with itself. From that information, it's not hard to reconstruct the triangles. You know that a 45-45-90 triangle is an isosceles triangle, so it must have the side lengths where the same number goes with itself. And a 30-60-90 triangle has one side length smaller than the other, so the smaller side must be 1/2, and the larger side must be root 3 over 2, since root 3 is bigger than 1, and so root 3 over 2 is bigger than 1/2. Doing a visual check, you can easily fill in the angles. The smaller angle must be the 30-degree angle, and the larger one must be the 60-degree one. In this video, we computed the sine and cosine of three special angles: 30 degrees, 45 degrees, and 60 degrees. This video defines sine and cosine in terms of points on the unit circle. A unit circle is a circle with radius 1. Up to now, we've defined sine and cosine and tangent in terms of right triangles. For example, to find sine of 14 degrees, in theory, you could draw a right triangle with an angle of 14 degrees, and then calculate the sine as the length of the opposite side over the length of the hypotenuse. But if we use this method to try to compute sine of 120 degrees, things go horribly wrong. When we draw this 120-degree angle and this right angle, there's no way to complete this picture to get a right triangle. So instead, we're going to use a unit circle, that is, a circle of radius 1. The figure below illustrates how right triangles and a unit circle are related. If you draw right triangles with larger of hypotenuse 1, with larger and larger angles, then the top vertex sweeps out part of a unit circle. Let's look at this relationship in more detail. In this figure, I've drawn a right triangle inside a unit circle. The hypotenuse of the triangle is the radius of the circle, which is 1. One vertex of the right triangle is at the origin, and another vertex of the right triangle is at the edge of the circle. I'm going to call the coordinates of that vertex A, B. Now the base of this right triangle has length A, the x-coordinate, and the height of the right triangle is B, the y-coordinate. If I use the right triangle definition of sine and cosine of theta, this right here is the angle theta, then cosine of theta is adjacent over hypotenuse. So that's A over 1, or A. Notice that A also represents the x-coordinate of this point on the unit circle at angle theta from the x-axis. I'll write that down. For sine of theta, if I use the right triangle definition, that's opposite over hypotenuse, so B over 1, which is just B. But B also represents the y-coordinate of this point on the unit circle at angle theta. For tangent theta, if we use the right triangle definition, it's opposite over adjacent, so that's B over A. I can think of that as the y-coordinate of the point over the x-coordinate of the point. Now for angles theta that can't be part of a right triangle because they're too big, they're bigger than 90 degrees, like now I'll call this angle here theta, I can still use this idea of x and y coordinates to calculate the sine and cosine of theta. So if I just mark this point on the end of this line at angle theta, if I mark that to have coordinates x and y, then cosine theta I'm still going to define as the x-coordinate of this point, sine theta as the y-coordinate, and tangent theta as the ratio of the y-coordinate over the x-coordinate. When we use this unit circle definition, we always draw theta starting from the positive x-axis and going counterclockwise. Let's use this unit circle definition to calculate sine, cosine, and tangent of this angle phi. In our figure, we have a unit circle, and these numbers are supposed to represent the x and y coordinates of this point on the unit circle at the endpoint of this line segment that lies at angle phi from the positive x-axis. Sine phi is equal to the y-coordinate. Cosine phi is equal to the x-coordinate. And tangent of phi is given by the ratio of the two, which works out to negative 0.3639 up to 4 decimal places. This video gives a method for calculating sine, cosine, and tangent in terms of the unit circle. Starting from the positive x-axis, you draw the angle theta going counterclockwise. You look at the coordinates of the point on the unit circle where that angle ends, and cosine of that angle theta is the x-coordinate, sine of theta is the y-coordinate, and tangent of theta is the ratio. This video gives 3 properties of the trig functions sine and cosine that can be deduced from the unit circle definition. Recall that the unit circle definition of sine and cosine for an angle theta is that cosine theta is the x-coordinate and sine of theta is the y-coordinate for the point on the unit circle at angle theta. The first property is what I call the periodic property. This says that the values of cosine and sine are periodic with period 2 pi, and what that means is that if you take cosine of an angle plus 2 pi, you get the same thing as just if you took cosine of the angle. So when we write this down, we're assuming that theta is measured in radians. If we want to measure theta in degrees, the similar statement is that cosine of theta plus 360 degrees is equal to cosine of theta. We can make the same statements for sine. Sine of an angle plus 2 pi is equal to sine of the original angle, here the angle being measured in radians. If we want to measure the angle in degrees, the statement is that sine of theta plus 360 is equal to sine of theta. We can see why this is true from the unit circle definition of sine and cosine. If this is our angle theta, then theta plus 2 pi, the plus 2 pi adds a full turn around the unit circle to our angle, so we end up at the same place. Theta and theta plus 2 pi are just two different names for the same location on the unit circle. And since sine and cosine give you the y and x coordinates of that point on the unit circle, they have to have the same value. Similarly, if we consider an angle theta and an angle theta minus 2 pi, the minus 2 pi means we go the other direction around the unit circle, clockwise. We still end up in the same place, and therefore cosine of theta minus 2 pi, the x-coordinate of that position, is the same thing as cosine of theta. Sine of theta minus 2 pi is the same thing as sine of theta. The same statements hold if we add or subtract multiples of 2 pi. For example, cosine of theta plus 4 pi is still the same thing as cosine of theta. This time we've just gone 2 turns around the unit circle and still gotten back to the same place. So if we want to find cosine of 5 pi, that's the same thing as cosine of pi plus 4 pi, which is the same thing as cosine of pi. Thinking about the unit circle, pi is halfway around the unit circle, so cosine of pi means the x-coordinate of this point right here. Well, that point has coordinates -1, 0, so cosine of pi must be -1. If I want to take sine of -420 degrees, well, that's sine of -360 degrees minus 60 degrees, which is the same thing as sine of -60 degrees. Thinking about the unit circle, minus 60 degrees means I start at the positive x-axis and go clockwise by 60 degrees. That lands me about right here, and so that's one of the special angles that has an x-coordinate of 1/2, a y-coordinate of -√3/2, and therefore sine of -60 is -√3/2, the y-coordinate. The next property I call the even-odd property. It says that cosine is an even function, which means that cosine of negative theta is the same thing as cosine of theta, while sine is an odd function, which means that sine of negative theta is the negative of sine of theta. To see why this is true, let's look at an angle theta and the angle negative theta. A negative angle means you go in the clockwise instead of counterclockwise direction from the positive x-axis. The coordinates of this point, by definition, are cosine theta, sine theta, whereas the coordinates of this point are cosine negative theta, sine of negative theta. But by symmetry, these 2 points have the exact same x-coordinate, and therefore cosine of theta must equal cosine of negative theta, while their y-coordinates have the same magnitude but opposite signs. This one's positive and this one's negative. Therefore, sine of negative theta is the negative of sine of theta. Let's figure out if tan of theta is an even or odd function. Well, we know that tan of negative theta, tangent by definition, is sine over cosine. Well, we know that sine of negative theta is the negative of sine of theta, whereas cosine of negative theta is cosine of theta. Therefore, we're getting negative sine theta over cosine theta, which is negative tan of theta. Since tan of negative theta is the negative of tan of theta, tan theta is an odd function. The last property on this video is the Pythagorean property, which says that cosine of theta squared plus sine of theta squared is equal to 1. A lot of times this property is written with the shorthand notation cosine squared theta plus sine squared theta equals 1. But this notation cosine squared theta just means you take cosine of theta and square it. This property is called the Pythagorean property because it comes from the Pythagorean theorem. Let me draw a right triangle on the unit circle. I'll call this angle theta, so the coordinates of this endpoint here are cosine theta, sine theta. Since this is supposed to be a unit circle, the hypotenuse of my right triangle has length 1. The base of my right triangle is just cosine theta, same thing as the x-coordinate of this point. And the height of my triangle is the y-coordinate of the point, sine theta. Now the Pythagorean theorem says that this side length squared plus that side length squared equals 1 squared. Since 1 squared is the same thing as 1, that gives me the Pythagorean property. The Pythagorean property is handy for computing values of cosine given values of sine and vice versa. In this problem, we're told that sine of t is negative 2/7, and t is an angle that lies in quadrant 3. When we say the angle lies in quadrant 3, that means the terminal side of the angle lies here in quadrant 3. One way to find cosine of t is to use the fact that cosine squared t plus sine squared t is equal to 1. That is, cosine of t squared plus negative 2/7 squared is equal to 1. I can write this as cosine of t squared plus 4/49 is equal to 1, and so cosine of t squared is equal to 1 minus 4/49, which is 45/49. Taking the square root of both sides, that gives me that cosine t is plus or minus the square root of 45 over 49. That's plus or minus the square root of 45 over 7. Now, since we're in the third quadrant, we know that cosine of t, which represents the x-coordinate of this point, must also be negative. Therefore, cosine of t is going to be negative square root of 45 over 7. It's also possible to solve this problem using the Pythagorean theorem for right triangles directly. If we look at the fact that sine of t is negative 2/7 and ignore the negative sign for now, we can think of this information as telling us that we have a right triangle, the angle theta, whose opposite side is 2 and whose hypotenuse is 7. If we call this side here a, then Pythagorean theorem tells us a squared plus 2 squared is 7 squared. So a squared plus 4 is 49. So a squared is 45, and a is plus or minus the square root of 45. Since I'm worrying about a triangle, I'm going to use the positive value. Now, cosine of t is going to be adjacent over hypotenuse. So that's going to be the square root of 45 over 7. Now I go back to thinking about positive and negative signs, and I notice that since I'm in the third quadrant, my cosine needs to be negative, so I just stick a negative sign in front. This alternative solution uses many of the same ideas as the previous solution, and ultimately gets us the same answer. This video gives 3 properties of trig functions: the periodic property, the even-odd property, and the Pythagorean property. This video is about the graphs of sine and cosine. I want to graph the functions y equals cosine t and y equals sine t, where t is in radians. I'm going to think of this being the t-axis and this being the y-axis. One way to do this is to plot points. So I'll fill in this chart using my knowledge of special angles on the unit circle. These points will be easier to graph if I convert them all to decimals. Now I'll plot the points for cosine and connect the dots to get a graph of y equals cosine t from t equals 0 to t equals 2 pi. To continue the graph for t values less than 0 or bigger than 2 pi, I could plot more points, or I could just use the fact that the cosine values repeat. If I add or subtract 2 pi to my angle t, I'll be at the same place on the unit circle, so my cosine will be exactly the same. Therefore, my values of cosine, which are represented by my y values on this graph, repeat themselves. For example, when my t value is 2 pi plus pi over 6, about like here, its cosine is the same as the cosine of just pi over 6. So I'll take this dot here and repeat it over here. Similarly, when t is like 2 pi plus pi over 4, I get the same value of cosine as when it's just pi over 4. So this dot is going to repeat. And I can continue repeating all my dots. This one repeats over here at 2 pi plus, say, pi over 3. And so my whole graph will repeat something like this. It also repeats on this side, something like this, since subtracting 2 pi from my t values will also give me the same value of cosine. We can also plot points to get a graph for sine and extend it by repetition. Going forward, I'll usually write the functions sine and cosine as y equals cosine of x and y equals sine of x. When I write it this way, notice that x now refers to an angle, while y refers to a value of cosine or sine. That's a different meaning of x and y compared to when we're talking about the unit circle, where x refers to the cosine value and y refers to the sine value. Now, let's look at some properties of the graphs of sine and cosine. The first thing you might notice is that the graph of cosine and the graph of sine are super similar to each other. In fact, you can think of the graph of cosine as just being the graph of sine shifted to the left by pi over 2. So we can write cosine of x as the sine function of x plus pi over 2, since adding pi over 2 on the inside moves the graph horizontally to the left by pi over 2. Or we can think of the graph of sine as being constructed from the graph of cosine by shifting the cosine graph right by pi over 2. That means we can write sine of x as equal to cosine of x minus pi over 2, since subtracting pi over 2 on the inside shifts the cosine graph to the right by pi over 2. Next, let's look at domain and range. The domain of sine and cosine is all real numbers. I'll write that as negative infinity to infinity, but the range is just from negative 1 to 1. That makes sense because sine and cosine come from the unit circle. The input values for the domain come from angles, and you can use any number as an angle, positive, negative, as big as you want, just by wrapping a lot of times around the circle. The output values for the range, that is the actual values of sine and cosine, come from the coordinates on the unit circle, and those coordinates can't be any bigger than 1 or any smaller than negative 1. So that gives us our range. As far as even and odd behavior, you can tell from the graph, here's cosine, that it's symmetric with respect to the y-axis, and so it must be even, whereas the graph of sine is symmetric with respect to the origin and must be odd. The absolute maximum values of these two functions is 1, and the absolute minimum value is negative 1. We can also use the words midline, amplitude, and period to describe these two functions. The midline is the horizontal line halfway in between the maximum and minimum points. Here, the midline is y equals 0. The amplitude is the vertical distance between a maximum point and the midline. You can also think of the amplitude as the vertical distance between a minimum point and the midline, or as half the vertical distance between a min point and a max point. For the cosine function and the sine function, the amplitude is 1. A periodic function is a function that repeats at regular horizontal intervals. The horizontal length of the smallest repeating unit is called the period. For y equals cosine of x, the period is 2 pi. Notice that the period is the horizontal distance between successive peaks, or maximum points, or between successive troughs, or minimum points. Algebraically, we can write cosine of x plus 2 pi equals cosine of x, and sine of x plus 2 pi equals sine of x to indicate that the functions repeat themselves over an interval of 2 pi and have a period of 2 pi. In this video, we graphed y equals cosine of x and y equals sine of x, and observed that they both have a midline at y equals 0, an amplitude of 1, and a period of 2 pi. Sinusoidal functions are functions that are related to sine and cosine by transformations, like stretching and shrinking and shifting. This video is about graphing these functions. Let's start by graphing the function y equals 3 sine of 2x. This function is related to the function y equals sine x, so I'll graph that first. Now the 3 on the outside stretches this graph vertically by a factor of 3, while the 2 on the inside compresses it horizontally by a factor of 1/2. If instead I want to graph y equals 3 sine 2x plus 1, this plus 1 on the outside shifts everything up by 1 unit. Let's compare the midline, amplitude, and period of our original y equals sine x, our transformed y equals 3 sine 2x, and our further transformed y equals 3 sine 2x plus 1. The original sine has a midline at y equals 0, an amplitude of 1, and a period of 2 pi. For the transformed function, y equals 3 times sine of 2x, the 2 on the inside shrinks everything horizontally by a factor of 1/2. So it changes the period of 2 pi into a period of 1/2 times 2 pi, which is pi. Since the 2 on the inside only affects x values and horizontal distances, it doesn't affect the midline, which is a y value, or the amplitude, which is a vertical distance. But the 3 on the outside does affect these things. Well, in particular, it affects the amplitude. Since everything is stretched out vertically by a factor of 3, the amplitude of 1 gets stretched to an amplitude of 3. In this case, the midline doesn't actually change because multiplying a y value of 0 by 3 is still a y value of 0. Now on the third function, we've taken the second function and added 1 on the outside, so that shifts everything up by 1. Therefore, instead of having a midline at y equals 0, we now have a midline at y equals 1. The amplitude doesn't change, though. It's still 3, because shifting everything up by 1 doesn't affect the distance between the midline and the maximum point. Also, the period is still pi, since the period is a horizontal measure, and adding 1 on the outside only affects vertical things. Next, let's graph the function y equals 3 times sine of 2 times quantity x minus pi over 4. This function is very closely related to the first function we graphed on the previous page. That was y equals 3 sine of 2x. In fact, if we give the name f of x to that function, and maybe we can call g of x this other function, then we can get g of x by taking f of x and plugging in x minus pi over 4 in for x. In other words, g of x is f of x minus pi over 4. This relationship gives me an idea for graphing g of x, the function we want to graph. We can first graph f of x. We already did that on the previous page. And then we can shift its graph to the right by pi over 4, because that's what you do when you subtract a number on the inside of a function. So here's the graph of y equals 3 sine 2x. Recall that it's just the graph of sine stretched vertically by a factor of 3 and shrunk horizontally by a factor of 1/2. Now, to graph the function that I want, I'm going to shift this graph over by pi over 4 to the right. Notice that since I had my function written in factored form, I could just read off the horizontal shift. But if I had written it instead as y equals 3 sine 2x minus pi over 2, which is algebraically equivalent, it would be easy to get confused and think that I needed to shift over by pi over 2. So it's best to factor first before figuring out what the shift is. We're factoring out the coefficient of x. If instead we wanted to graph this function, same as the one we just graphed, it's just with a -1 on the outside, that -1 would just bring everything down by 1. Let's take a moment to look at midline, amplitude, and period for the original parent function y equals sine of x and our final transformed function y equals 3 sine of 2 times quantity x minus pi over 4 minus 1. Our original sine function has midline at y equals 0, amplitude of 1, and period of 2 pi. For our transformed function, the 3 on the outside stretches vertically, so it makes the amplitude 3. The -1 on the outside shifts everything down by 1, so it brings the midline y equals 0 down to y equals -1. The 2 on the inside shrinks everything horizontally by a factor of 1/2, so the period becomes 1/2 times 2 pi, which is pi. Finally, there's a horizontal shift going on. Our transformed function shifts to the right by pi over 4. This horizontal shift is sometimes called the phase shift. The function we just analyzed was y equals 3 sine 2 x minus pi over 4 minus 1, which could also be written as y equals 3 sine 2x minus pi over 2 minus 1. This is a function of the form y equals a sine bx minus c plus d, where b is positive. If we have a function of this form, or the similar function with cosine in it, then we know that the midline is going to be at y equals d. That's because the original midline of sine or cosine at y equals 0 gets shifted up by d. We know that the amplitude is going to be a, because this a multiplied on the outside stretches everything vertically by a factor of a. To be a little more accurate, we should say the amplitude is the absolute value of a in case a is negative. If a is negative, then that amounts to a vertical reflection, or a reflection over the x-axis. We know that the period of the original sine or cosine is 2 pi, and we know that this factor of b amounts to a horizontal shrink by a factor of 1 over b, or I guess it could be a horizontal stretch by a factor of 1 over b if b is less than 1. So because we're starting with a period of 2 pi, and we're multiplying by 1 over b, our new period is going to be 2 pi over b. The trickiest thing is the horizontal shift. And to get that right, I like to factor out this b from my equation. So instead of writing y equals a cosine bx minus c plus d, I'm going to write y equals a cosine b times quantity x minus c over b plus d. Similarly, if it's a sine function, I write y equals a sine b times x minus quantity c over b plus d. Then I can read off the horizontal shift as c over b, and that'll be a shift to the right if c over b is positive and a shift to the left if c over b is negative. This might seem backwards from what you're used to, but it's because we have that minus sign there. So if c over b is positive, we're actually subtracting on the inside, so that shifts right. If c of b over b is negative, minus a negative is actually adding something, and that's why it shifts it to the left. So as one final example, say I wanted to graph y equals 1/3 cosine of 1/2 x plus 3 minus 5. That would have a midline at y equals minus 5, an amplitude of 1/3, a period of 2 pi divided by 1/2, which is 4 pi, and a horizontal shift. Better rewrite this. A horizontal shift of 6 units to the left. The horizontal shift is sometimes called the phase shift. And that's all for graphs of sinusoidal functions. This video is about graphing the trig functions tangent, secant, cotangent, and cosecant. To gain an intuition for the graph of y equals tangent of x, I think it's handy to look at the slope of a line at angle theta on the unit circle. The slope of this line is the rise over the run, but the rise is given by sine of theta, and the run is given by cosine of theta, so the slope is given by sine theta over cosine theta, which is simply tan of theta. So if I want to graph y equals tan of x, I can think of x as being the angle and y as being the slope of the line at that angle. Notice that if the angle is 0, the slope is 0, but as the angle increases towards pi over 2, the slope gets bigger and bigger, heading towards infinity. As the angle goes from 0 towards negative pi over 2, the slope is getting negative and heading towards negative infinity. At exactly pi over 2 and negative pi over 2, we have a vertical line, and so the slope is undefined. Using this information, let's graph a rough sketch of y equals tan x. Remember, we're thinking of x as the angle and y as the slope. We're going to go between an angle of negative pi over 2 and pi over 2. So we said that the slope was 0 when the angle's 0, and then it heads up towards positive infinity as we go towards, the angle goes towards pi over 2 with an undefined value at pi over 2. It goes negative, heading towards negative infinity as the angle heads towards negative pi over 2, also with an undefined value at negative pi over 2. You can also verify that for angles slightly bigger than pi over 2, we have the same line as for angles that are approaching negative pi over 2, and therefore this picture repeats, and it turns out that tangent is periodic with period not 2 pi like sine and cosine, but just pi. The period of pi makes sense because if you take a line and rotate it by 180 degrees, it's the same line with the same slope and therefore has the same value of tangent. In this graph of y equals tan x, notice that the x-intercepts are at values of x of the form negative 2 pi negative pi, 0, pi, 2 pi, etc., you can write that as pi times k, where k is an integer, that is, a positive or negative whole number, or 0. This makes a lot of sense because tangent of x is sine of x over cosine of x. And so you're going to get x-intercepts. That's where y is 0, which is where the numerator is 0. And sine x is 0 at values of the form pi, 2 pi, and so on. From the graph, you can see the vertical asymptotes are at values like negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. These values can be written as pi over 2 times k, where k is an odd integer. Again, this makes sense from the definition of tangent, since vertical asymptotes will occur where the denominator is 0 and cosine x is 0 at numbers like negative pi over 2, pi over 2, 3 pi over 2, and so on. The domain of tangent is the x-axis for which it's defined, so that's going to be everything except for the vertical asymptotes. We can write that as x such that x is not equal to pi over 2 times k, for k an odd integer. The range, or the y values, go all the way from negative infinity to infinity, and the period, as we mentioned previously, is pi. Since the smallest repeating unit has a horizontal width of pi. To graph y equals secant x, I'm going to remember that secant is 1 over cosine. So if I start with a graph of cosine, I can take the reciprocal of the y values to get the graph of secant. The reciprocal of 1 is 1. The reciprocal of 0 is undefined, so I'm not going to have a value at pi over 2, negative pi over 2, 3 pi over 2, or negative 3 pi over 2. When I take the reciprocal of numbers just less than 1, I'm going to get numbers just greater than 1. But if I take the reciprocal of positive numbers getting close to 0, I'm going to get really big positive numbers going up towards infinity. Similarly, on the other side, over here, I have numbers close to 0 but negative, so their reciprocals will be negative numbers heading towards negative infinity. The reciprocal of negative 1 is negative 1, and similarly here. So I'm getting kind of positive and negative buckets and upside down buckets as the graph of my secant. Notice that secant has a period of 2 pi, which makes sense since cosine has a period of 2 pi. It has a range that goes from negative infinity to negative 1 inclusive, and from 1 to infinity. That makes sense because the range of cosine is between 1 and negative 1, and we're taking the reciprocal of those values. The domain is everything except for the vertical asymptotes. Now the vertical asymptotes are where cosine is 0. So that is at values of the form pi over 2, 3 pi over 2, etc. That's values of the form pi over 2k, where k is an odd integer. So the domain is going to be x values such that x is not equal to pi over 2k for k, an odd integer. The x-intercepts of secant, well, it doesn't have any because you can't take 1 over something and get the number 0 for your y value. We've seen the graphs of y equals tan x and y equals secant x. This is the graph of y equals cotangent x. It looks similar to the graph of tangent x. It's just a decreasing function instead of an increasing one, and it has its vertical asymptotes and its x-intercepts in different places. Finally, this green graph is the graph of y equals cosecant x. It's related to the graph of sine x, since cosecant is 1 over sine x. And in fact, if I draw the graph of sine x in between, you can see how it kind of bounces off because it's the reciprocal. I encourage you to memorize the general shape of these graphs. You can always figure out the details by thinking about how they're related to the graphs of cosine of x and sine x. This video is about the graphs of transformations of tangent, secant, cotangent, and cosecant. Before I graph this fancy function, I'm going to graph the related parent function, y equals cosecant of x. Recall that cosecant of x is 1 over sine of x, so the graph of cosecant of x has vertical asymptotes where sine of x is 0. That puts the vertical asymptotes at pi, 2 pi, 0, and so on. Cosecant of x is 1 where sine is 1, so here, and so it looks something like this. Now when I graph my fancy function, I know that the 2 on the outside does a vertical stretch by 2. The plus 1 shifts up by 1. The pi means everything shrinks horizontally by 1 over pi, and so the period, instead of being 2 pi, like it is for cosecant, it's going to be 2 pi divided by pi, which is 2. Finally, this pi over 2 has to do with a horizontal shift, but in order to see by how much we horizontal shift, we need to factor out the pi first. So if I rewrite my function as 2 times cosecant pi times x plus a half plus 1, I can see that the horizontal shift is 1/2 to the left. Let me do those transformations in pieces. First, I'll do the vertical motions, so I'll leave the horizontal axis as is. I'll stretch by a factor of 2, and now I'll shift up by 1. Next, I'll worry about the horizontal motion. Instead of a period of 2 pi, I'm going to have a period of 2. But in addition, everything is going to be shifted left by 1/2. So instead of having my vertical asymptotes at 0, pi, 2 pi, and so on, they would be at 0, 1, 2, and so on, except everything's shifted over by 1/2. So that means the vertical asymptotes will actually be at negative 1/2, 1/2, 1.5, and so on. Another way to find the vertical asymptotes is by noting that cosecant is 1 over sine. So therefore, cosecant pi x plus 1/2 does not exist when sine pi x plus 1/2 equals 0, i.e. when pi times x plus 1/2 is equal to a multiple of pi. Canceling the pi's and solving for x, that's when x is some number minus 1/2, so those are exactly the values of, say, 1/2, 3/2, 5/2, and so on that we've drawn. So once we've got the vertical asymptotes in place, we can see that our graph fits in between them. This purple piece got shrunk horizontally and shifted by 1/2, so it ends up hugging the x-axis. I'll draw it in right here. And all the other pieces also get shrunk horizontally and shifted. So my final graph looks something like this. In this next problem, we're given the graph and we need to find the equation. The shape of the graph and the fact that it's increasing tells us it must be a tangent graph. But y equals tan x by itself would have a period of pi. Let's check what our graph has a period of. We need to find the horizontal width of one complete cycle. It's probably easiest to measure if I sketch in the vertical asymptotes, which seem to run from an x value of -3 to an x value of 1, so that's a horizontal distance of 4. So our graph might be something more like tan of bx, where pi over b has to be 4. That means that pi equals 4b, and so b is pi over 4. So our graph is probably more closely related to y equals tan of pi over 4x. But if it were exactly y equals tan of pi over 4x, then that middle point right here would be at the origin. And instead, that middle point is at -1, 1. That means my tangent graph is shifted left by 1 and up by 1. The left by 1 I can accomplish by writing x plus 1 when I have the pi over 4 factored out. The up by 1 I get by writing a plus 1 on the outside. Now it's possible there might also be a vertical stretch factor out front. An easy way to check for that is by plugging in x equals 0 and seeing what kind of number out in front I might need to get this y-intercept of 2. So I'm going to write y equals a tan pi over 4 quantity x plus 1, plug in the point 0, 2, so that's 2 equals a tan pi over 4, 0 plus 1, and I can solve for a. Since tan of pi over 4 is just 1, this equation simplifies to 2 equals a times 1 plus 1, which means that a has to be 1. So in fact, this equation here is our final answer for this graph. To summarize, if we have a function of the form y equals a tan bx minus c plus d, the number a accomplishes a vertical stretch. The number b changes the period from pi to pi over b. The number d shifts vertically by d. And finally, to figure out what the number c is, we have to rewrite our equation in factored form, factoring out the b. And so we see that there's a phase shift right by c over b. The same things hold if instead of tangent, we have a graph of cotangent. We can say the same things for a graph of secant and a graph of cosecant. The only thing to be careful of is that b now changes the period from 2 pi to 2 pi over b, simply because the original period of secant and cosecant is 2 pi, whereas the original period of tan and cotan is just pi. If you know what the original graphs of tan, secant, cotangent, and cosecant look like, you can use your knowledge of transformations to graph more complicated functions. This video defines the standard inverse trig functions: sine inverse, cosine inverse, and tan inverse. In this crazy-looking graph, please focus first on the thin black line. This is a graph of y equals sine x. The graph of the inverse of a function can be found by flipping the graph of the original function over the line y equals x. I've drawn the flipped graph with this blue dotted line. But you'll notice that the blue dotted line is not the graph of a function because it violates the vertical line test. So in order to get a function that's the inverse of y equals sine x, we need to restrict the domain of sine of x. we'll restrict it to this piece that's drawn with a thick black line. If I invert that piece by flipping it over the line y equals x, I get the piece drawn with a red dotted line here. And that piece does satisfy the vertical line test, so it is in fact a function. Although regular sine x has domain from negative infinity to infinity, our restricted sine x has domain from negative pi over 2 to pi over 2. Its range is still from negative 1 to 1, just like the regular sine x, because I've taken the biggest possible piece of the graph whose flipped version is still a function. The inverse sine function is often written as arcsine of x. And since inverting a function reverses the roles of y and x, it reverses the domain and the range. So arcsine of x, the inverse function, has domain from negative 1 to 1 and range from negative pi over 2 to pi over 2, which seems plausible from the graph. Now an inverse function undoes the work of a function. So if the function sine takes angles theta to numbers x, then the inverse sine, or arcsine, takes numbers x to angles theta. For example, since sine of pi over 2 is 1, arcsine of 1 is pi over 2. And in general, the output of arcsine of x is the angle between negative pi over 2 and pi over 2, whose sine is x. Y is equal to arcsine x means that x is equal to sine of y. But since there are many angles y whose sine is x, right, they all differ by multiples of 2 pi, we specify also that y is between negative pi over 2 and pi over 2. That was the whole point of doing this domain restriction in order to get a well-defined inverse value. There's an alternate notation for inverse sine. Sometimes it's written as sine to the negative 1 of x. But this notation can be confusing, so be careful. In particular, sine to the negative 1 of x does not equal 1 over sine of x. 1 over sine of x, the reciprocal function, is another word for cosecant of x. But sine to the negative 1 of x is another word for arcsine of x, the inverse sine function, which is not the same thing as the reciprocal function. Let's go through the same process to build an inverse cosine function. We start with a graph of cosine of x. We flip it over the line y equals x to get the blue dotted line, but the blue dotted line is not a function, so we go back and restrict the domain for our original cosine of x to just be between 0 and pi. The resulting red graph now satisfies the vertical line test, so it's a proper inverse function. Our restricted cosine has domain from 0 to pi and range from negative 1 to 1, and so our inverse function, arccosine, has domain from negative 1 to 1 and range from 0 to pi. Since cosine takes us from angles to numbers, arccosine takes us from numbers back to angles. For example, cosine of pi over 4 is the square root of 2 over 2, so arccosine of the square root of 2 over 2 is equal to pi over 4. Arccosine of x is the angle between 0 and pi, whose cosine is x. In other words, y equals arccosine of x means that x is equal to cosine of y, and y is between 0 and pi, since otherwise there'd be lots of possible answers for an angle y whose cosine is x. The alternative notation for arccosine is cosine inverse. And again, we have to be careful. Cosine to the negative 1x is not the same thing as 1 over cosine of x. 1 over cosine of x is also called secant of x. Cosine to the negative 1x means arccosine, the inverse function, and these two things are not the same. Finally, let's take a look at inverse tangent function. Here's a graph of tangent in black. These vertical lines aren't really part of the function, they're just vertical asymptotes. So in order to get an actual function, when we flip over the line y equals x, we take just one piece of the tangent function. Here we've taken the piece marked in black. When we flip that over the line y equals x, we get this piece in red, which is actually a function because it satisfies the vertical line test. Now you might ask, would it be possible to pick a different piece of the tangent function to invert? And the answer is yes, we could do that. And on another planet, maybe mathematicians do that. But on our planet, we use the convention that we pick this piece of tangent to invert, which is kind of a convenient choice since it's centered here around the origin. In the previous two examples, our choice of restricted domain for sine and for cosine was also a convention that led to a conveniently defined inverse function. In any case, based on our choice, our restricted tan function has domain from negative pi over 2 to pi over 2. We don't include the endpoints in that interval because our restricted tan function has vertical asymptotes at negative pi over 2 and pi over 2, so it's not defined there. The range of our restricted tan function is from negative infinity to infinity. Therefore, arctan of x has domain from negative infinity to infinity and range from negative pi over 2 to pi over 2. Once again, tangent is taking us from angles to numbers, so arctan is taking us from numbers to angles. For example, tangent of pi over 4 is 1, and therefore arctan of 1 is pi over 4. So arctan of x means the angle between negative pi over 2 and pi over 2 whose tangent is x. Y is equal to arctan x means that x is equal to tangent of y, and that y is between negative pi over 2 and pi over 2. The inverse tan function can also be written as tan to the minus 1 of x. And once again, tan inverse of x means the inverse trig function, arctan of x, and it's not equal to 1 over tan of x, which is called cotangent of x. And that's all for this video on the 3 basic inverse trig functions. Sine inverse x, also known as arcsine of x, cosine inverse x, also known as arccosine x, and tan inverse x, also known as arctan x. This video is an introduction to solving trig equations. Let's start with the equation 2 cosine x plus 1 equals 0. I want to find all the solutions in the interval from 0 to 2 pi, and then get a general formula for all solutions, not just those in that interval. Let me start by rewriting this equation to isolate the tricky part, which is cosine of x. So I'm going to write 2 cosine x equals negative 1, and then divide both sides by 2. Now I'm looking for the angles x between 0 and 2 pi, whose cosine is negative 1/2. Since negative 1/2 is one of the special values on the unit circle, I can use my knowledge of the unit circle to see that the angle between 0 and 2 pi must be either 2 pi over 3 or 4 pi over 3. My answer needs to include both of these values. There are no other spots on the unit circle whose cosine is negative 1/2, But there are more angles because we can always take one of these angles and add multiples of 2 pi to it. So if I want to find all solutions, I can take these two principal solutions, 2 pi over 3 and 4 pi over 3, and simply add multiples of 2 pi to them. For example, 2 pi over 3 plus 2 pi, or 2 pi over 3 minus 2 pi, 2 pi over 3 plus 4 pi, and so on. A much more efficient way to write this is to write 2 pi over 3 plus 2 pi times k, for k any integer. That is, any positive or negative whole number or 0. Similarly, I can write 4 pi over 3 plus 2 pi k to capture all solutions based on the principal solution 4 pi over 3 by adding and subtracting multiples of 2 pi. This is my final solution. Next, let's look at a trig equation involving tangent. As usual, I'm going to start out by cleaning things up and isolating the tricky part, which in this case is tangent. So let me add tangent to both sides. That'll give me 3 tan x equals the square root of 3, and so tan x is the square root of 3 over 3. The square root of 3 over 3 looks suspiciously similar to the value of square root of 3 over 2, which is a special value on my unit circle. So my suspicion is that my unit circle will again help me find this value of x without a calculator. Recall that tan x is sine x over cosine x. So I'm looking for angles on the unit circle between 0 and 2 pi, where the ratio of sine over cosine will give me square root of 3 over 3. I actually only need to look in the first quadrant and the third quadrant, because those are the quadrants where tangent is positive. And I really only need to look at angles whose either sine or cosine has a square root of 3 in it. So by trial and error, I can see that tan pi over 6, which is sine pi over 6 over cosine pi over 6, will give me 1/2 over root 3 over 2. That's the same thing as 1/2 times 2 over root 3, which is 1 over root 3. If I rationalize that, I get root 3 over 3. So that value works. If I try tan of pi over 3 instead, I get root 3, which is not equal to root 3 over 3. So pi over 3 doesn't work. Similarly, I can work out the values in the third quadrant and see that 7 pi over 6 works, but 4 pi over 3 does not. So my answer to part A includes just the two values, pi over 6 and 7 pi over 6. Now, if I want to find all solutions, not just those in the interval from 0 to 2 pi, I notice that I can take one of these principal solutions and add multiples of 2 pi to it, because that'll give me the same angle. So I get pi over 6 plus 2 pi k, and 7 pi over 6 plus 2 pi k for k any integer. This is a correct answer, but it's not as simple as it could be. Notice that 7 pi over 6, over here on the unit circle, is exactly pi more than pi over 6. So instead of taking both of these and adding multiples of 2 pi to them, I could get all the same answers by just taking one of them and adding multiples of pi to it. So a more efficient answer is to say that x equals pi over 6 plus pi times k for k any integer. This will still capture all the same solutions, because when k is even, I'll get this family of solutions, and when k is odd, I'll get this family. For example, when k is 1, pi over 6 plus 1 times pi is just the original 7 pi over 6. if you think about the fact that tangent has a period of pi instead of 2 pi, it makes a lot of sense that you should be able to write the solutions in this form. In this video, we solved basic trig equations by first isolating sine or tangent, or the same thing would work with cosine, and then using the unit circle to find principal solutions. Principal solutions are just solutions between 0 and 2 pi. And then adding multiples of 2 pi to these principal solutions to get all solutions. For tangent, we noticed that it was equivalent to just use one principal solution and add multiples of pi instead of 2 pi. In a previous video, we looked at trig equations that could be solved using the unit circle. In this video, we'll solve trig equations that don't involve special values on the unit circle and require a calculator instead to solve. Let's look at the equation 2 cosine t equals 1 minus cosine t. As usual, I'll start by simplifying and isolating cosine. Adding cosine to both sides, I get 3 cosine t equals 1, and dividing by 3 gives cosine t equals 1/3. Now 1/3 is not one of my special values on the unit circle, but I can locate it approximately. Cosine represents the x value of a point on the unit circle, so I'm looking for a point on the unit circle whose x-coordinate is approximately 1/3, so maybe right here, and the symmetric angle right here. Those are angles in the first and fourth quadrants. To get a decimal approximation for one of these angles, I can take arc cosine of both sides of my equation. This gives me t equals arc cosine of 1/3, which, using my calculator on radian mode, I get a decimal approximation of 1.2310 up to 4 decimal places. It's important to use radian mode here, since by convention, the answers to trig equations are expected to be in radians unless otherwise specified. It's also important to notice that these two equations are not precisely the same thing. Since cosine t equals 1/3 has infinitely many solutions, if we don't restrict to a certain interval, and even if we restrict to the interval 0 to 2 pi, it still has 2 different solutions. On the other hand, arc t equals arc cosine of 1/3 has only one solution, and that solution lies between the angles of 0 and pi. So this angle here, the 1.2310 radians, must be giving us this angle, since it's got to be an angle between 0 and pi. And to get the other angle, this one, we can use the symmetry of the situation. This angle and this angle are the same size, so to get all the way around to here, we can go all the way to pi minus our 1.2310 radians. Using our calculator again, we can compute that 2 pi minus 1.2310 radians is equal to 5.0522 radians. So our two solutions on our interval from 0 to 2 pi are given by 1.2310 and 5.0522 radians. Let me emphasize that we found the second solution by taking 2 pi minus the first solution. Now it's straightforward to find all solutions. We can just take our two principal solutions and add multiples of 2 pi. It can be helpful to look at this solution graphically. To solve our equation cosine t equals 1/3, we want to know where this graph of y equals cosine of t intersects the horizontal line at y equals 1/3. This intersection point here corresponds to our first solution of 1.2310 radians. This intersection point here corresponds to our second solution. Notice that it occurs at a t-value that's 2 pi minus this t-value here. And all the other intersection points correspond to those first two intersection points shifted over by multiples of 2 pi. Next, let's look at the equation 4 sine x minus 1 equals 2. I'll start by rewriting this as 4 sine x equals 3, which is equivalent to sine x equals 3/4. Although 3/4 is not a special value on the unit circle, we can still use the unit circle to get oriented and see how many solutions there should be in the interval from 0 to 2 pi. Since sine represents the y-coordinate of a point on the unit circle, we're looking for points on the unit circle whose y-coordinate is 3/4. So that might be 3/4 might be about here, so that would be an angle about right here and about right here, so in the first and second quadrants. Let's take the arcsine of both sides to find one of those angles. I'm getting one of the angles to be arcsine of 3/4, which my calculator says is 0.8481 radians. That must be this angle here. To get the other angle, I can use symmetry. Since this angle here, you can get by going a full pi minus my previous angle. Pi minus 0.8481 is equal to 2.2935. So that's my second angle. Notice that this time, to get the second angle, we use pi minus the first angle, not 2 pi minus the first angle like we did for cosine. Once again, we can find all solutions simply by adding multiples of 2 pi. We can also locate these solutions on a graph of sine. We're looking for where the graph of y equals sine of x intersects with the horizontal line at y equals 3/4. And we can see that we have these two solutions, where the second one, its x value is pi minus the x value of this one. And then we have all these additional solutions that we can get by shifting over by positive and negative multiples of 2 pi from the first two. Finally, let's solve the equation tan x equals 4. If we simply take x to be tan inverse of 4, which is 1.3258 radians, we'll get a single solution. But thinking about the graph of tangent and intersecting that graph with the horizontal line y equals 4, we see that there should actually be two solutions in the interval from 0 to 2 pi. This makes sense because the period of tangent is pi, so any one solution will get repeated by intervals of pi. It also makes sense by thinking about the unit circle. Tangent, which can be thought of as the slope of a line at angle theta, takes on all positive real values both in the first quadrant and the third quadrant. So there are going to be two places on the unit circle where the tangent is 4. We've already found this one. To find the other one, we just need to add pi. This gives us our answer for the interval 0 to 2 pi, and we can add multiples of 2 pi to get all other solutions. Or, if we want to be more efficient, we can just write the first solution plus multiples of pi instead of 2 pi. Because these two solutions differ by exactly pi, taking the first solution and then adding multiples of pi will capture all solutions corresponding to both of these principal solutions. To summarize, to find all solutions to cosine t equals m, we need to find first cosine inverse of m, then take 2 pi minus this solution, and add multiples of 2 pi to both of those. To find solutions to the equation sine t equals n, we can start by taking sine inverse of n, using pi minus this, and adding multiples of 2 pi. To find all solutions to tangent t equals p, we can take t equal tan inverse of p and tan inverse of p plus pi and add multiples of 2 pi, or we can just take tan inverse of p and add multiples of pi. Although the examples that we saw were more simple than some, because for the examples we saw, the inverse trig function always landed us in the first quadrant, these methods will work more generally. That's all for this video on solving trig equations that require a calculator. This video is about identities involving trig functions, like sine and cosine. But I want to start with some examples that just involve quadratic functions. If I want to find the solutions to this equation, I can rewrite it, x squared minus 6x minus 7 equals 0, factor it, x minus 7 times x plus 1 equals 0, set the factors equal to 0, x minus 7 equals 0, or x plus 1 equals 0, and that gives me the solutions x equals 7 or x equals negative 1. Next, let's look at this more complicated equation. I'm going to try to solve that for x by multiplying out the right-hand side. Next, I'll combine terms on the right-hand side. So that gives me x squared minus 6x on both sides. Well, x squared minus 6x is equal to x squared minus 6x. That's true no matter what I plug in for x. And therefore, all values of x satisfy this equation. We can say that the solution set is all real numbers. This second equation is called an identity because it holds for all values of the variable. The first equation, on the other hand, is not an identity because it only holds for some values of x and not all values. Please pause the video for a moment and try to decide which of the following 3 equations are identities. That is, which of these equations hold for all values of the variable. To start out, you might want to test them by plugging in a few values of the variable and see if the equation holds. The first equation is not an identity. It does hold for some values of x. For example, if x equals 0, then sine of 2 times 0 is 0, and 2 times sine of 0 is also 0, so it does hold when x is 0. However, when x is, say, pi over 2, then sine of 2 times pi over 2, that's the same thing as sine of pi, which is 0, but 2 times sine of pi over 2, that's 2 times 1, or 2, and 0 is not equal to 2, so the equation does not hold for x equals pi over 2. Since it doesn't hold for all values of the variable, it's not an identity. The second equation is an identity. You can build some evidence for this by plugging in numbers. For example, cosine of 0 plus pi, which is negative 1, is the same thing as negative of cosine of 0. You can also check, for example, that cosine of pi over 6 plus pi is the same thing as negative cosine of pi over 6. But even if we check a zillion examples, that's just evidence. It's not a proof that the identity holds. We could have just gotten lucky with the values we picked. We can build a little bit stronger evidence by looking at graphs. I'm going to put theta on the x-axis, and if I graph y equals cosine of theta plus pi, that's just like the graph of cosine shifted over to the left by pi. On the other hand, if I graph y equals negative cosine theta, that's the graph of cosine theta reflected across the x-axis, which gives us the exact same graph. So graphing both sides gives us strong evidence that this equation is an identity. It holds for all values of theta. Now, the strongest evidence of all would be an algebraic proof, which we'll do later in the course once we have a formula for the cosine of a sum of two angles. In the meantime, let's look at equation C. It turns out equation C is an identity, and we could build evidence for it again by plugging in values for x or by graphing the left side and the right side separately and checking to see that the graphs coincided. But for this example, I'm going to go ahead and do an algebraic verification. In particular, I'm going to start with the left side of the equation and rewrite things until I get to the right side of the equation. The first thing I'll rewrite is secant and tangent in terms of their constituent functions, sine and cosine. Since secant of x is 1 over cosine x and tangent of x is sine x over cosine x, I can rewrite this expression as 1 over cosine x minus sine x times sine x over cosine x. I can clean up those fractions and write this as 1 over cosine x minus sine squared x over cosine x. Now I notice that I have two fractions with the same denominator. So I can pull them together as 1 minus sine squared x over cosine x. Next, I'm going to rewrite the numerator 1 minus sine squared x using the Pythagorean identity that says that cosine squared x plus sine squared x equals 1. And therefore, 1 minus sine squared x is equal to cosine squared x just by subtracting sine squared x from both sides. So I can replace my numerator, 1 minus sine squared x, with cosine squared x. And canceling one cosine from the top and from the bottom, that's the same thing as cosine of x, which is the right-hand side that I was trying to get to. So a combination of a bunch of algebra and the Pythagorean identity allows me to prove that this equation is true for all values of x. It's an identity. The best way to prove that an equation is an identity is to use algebra and to use other identities, like the Pythagorean identity, to rewrite one side of the equation till it looks like the other side. The best way to prove that an equation is not an identity is to plug in numbers that break the identity, that is, make the equation not true. Now, if you're just trying to decide if an equation is an identity or not, and not worried about proving it, then I recommend plugging in numbers or graphing the left and right sides to see if those graphs are the same. Recall that an identity is an equation that holds for all values of the variable. This video states and proves three identities called the Pythagorean identities. The first one is the familiar cosine squared theta plus sine squared theta equals 1. The second one says tan squared theta plus 1 equals secant squared theta. And the third one goes cotangent squared theta plus 1 equals cosecant squared theta. Let's start by proving that cosine squared theta plus sine squared theta equals 1. I'll do this by drawing the unit circle with a right triangle inside it. By the definition of sine and cosine, the x and y coordinates of this top point are cosine theta and sine theta. The hypotenuse of my triangle is 1, since that's the radius of my unit circle. Now the length of the base of my triangle is the same thing as the x-coordinate of this point. So that's equal to cosine theta. The height of this triangle is the same thing as the y-coordinate of this point. So that's sine theta. Now the Pythagorean theorem for right triangles says this side length squared plus that side length squared is equal to the hypotenuse squared. So by the Pythagorean theorem, we have that cosine theta squared plus sine theta squared equals 1 squared. I can rewrite that as cosine squared theta plus sine squared theta equals 1, since 1 squared is 1, and cosine squared theta is just a shorthand notation for cosine theta squared. That completes the proof of the first Pythagorean identity, at least in the case when the angle theta is in the first quadrant. In the case when the angle lies in a different quadrant, you can use symmetry to argue that the same identity holds, but I won't give the details here. To prove the next Pythagorean identity, tan squared theta plus 1 equals secant squared theta, let's use the first Pythagorean identity, which said that cosine squared theta plus sine squared theta equals 1. I'm going to divide both sides of this equation by cosine squared theta. Now I'm going to rewrite the left side by breaking apart the fraction into cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta. Now cosine squared theta over cosine squared theta is just 1. And I can rewrite the next fraction as sine of theta over cosine of theta squared. That's because when I square a fraction, I can just square the numerator and square the denominator, and sine squared theta is shorthand for sine of theta squared, similarly for cosine squared theta. Now on the other side of the equal sign, I can rewrite this fraction as 1 over cosine theta squared. Again, that's because when I square the fraction, I just get the 1 squared, which is 1, divided by the cosine theta squared, which is this. I'm almost done. Sine theta over cosine theta is the same thing as tangent theta. And 1 over cosine theta is the same thing as secant theta. Using the shorthand notation, this says 1 plus tan squared theta equals secant squared theta, which after rearranging is exactly the identity that we were looking for. The proof of the third Pythagorean identity is very similar. Once again, I'll start with the identity cosine squared theta plus sine squared theta equals 1, and this time I'll divide both sides by sine squared theta. I'll break up the fraction on the left, and now I'll rewrite my fractions as cosine theta over sine theta squared plus 1 equals 1 over sine theta squared. Cosine over sine can be written as cotangent, and 1 over sine can be written as cosecant. That gives me the identity that I'm looking for. We've now proved 3 trig identities. The first one we proved using the unit circle and the Pythagorean theorem. The second and third identities we proved by using the first identity and a bit of algebra. The sum and difference formulas are formulas for computing the sine of a sum of 2 angles, the cosine of a sum of 2 angles, the sine of a difference of 2 angles, and the cosine of a difference of 2 angles. Please pause the video for a moment to think about this question. Is it true that the sine of A plus B is equal to the sine of A plus the sine of B? No, it's not true. And we can see by an example, if we plug in, say, A equals pi over 2 and B equals pi, then the sine of pi over 2 plus pi is the same thing as the sine of 3 pi over 2, which is negative 1, whereas the sine of pi over 2 plus the sine of pi is equal to 1 plus 0, which is 1. Negative 1 is not equal to 1, so this equation does not hold for all values of A and B. There are a few values of a and b for which it does hold. For example, if a is 0 and b is 0, but it's not true in general. Instead, we need more complicated formulas. It turns out that the sine of the sum of two angles, a plus b, is given by sine of a cosine of b plus cosine of a sine of b. The cosine of a plus b is given by cosine a cosine b minus sine a sine b. I like to remember these with a song. Sine, cosine, cosine, sine, cosine, cosine, minus sine, sine. Please feel free to back up the video and sing along with me. I encourage you to memorize the two formulas for the sine of a sum of angles and the cosine of a sum of angles. Once you do, it's easy to figure out the sine and cosine of a difference of two angles. One way to do this is to think of sine of a minus b as sine of a plus negative b, and then use the angle sum formula. So this works out to sine cosine plus cosine sine. And now, if I use the fact that cosine is even, I know that cosine of negative b is cosine of b, and since sine is odd, sine of negative b is negative sine of b, so I can rewrite this as sine of a cosine of b minus cosine of a sine of b. Notice that this new formula for the difference is the same as the formula for the sum, it's just that plus sign turned into a minus sign. We can do the same trick for cosine of a minus b. That's cosine of a plus minus b, which is cosine a cosine minus b minus sine of a sine of negative b. Again, using even and odd properties, this gives us cosine a cosine b plus sine a sine b. Once again, the formula for the difference is almost exactly like the formula for the sum, just that minus sign has switched to a plus sign. Now let's use the angle sum formulas to find the exact value for the sine of 105 degrees. Now 105 degrees is not a special angle on the unit circle, but I can write it as the sum of two special angles. I can write it as 60 degrees plus 45 degrees. Therefore, the sine of 105 degrees is the sine of 60 plus 45, and now by the angle sum formula, this is sine, cosine, cosine, sine, and from my unit circle, I can figure out that sine of 60 degrees is root 3 over 2, cosine of 45 degrees, root 2 over 2, cosine of 60 degrees is 1/2, and sine of 45 degrees is root 2 over 2. So this simplifies to root 6 plus root 2 over 4. For our last example, let's find the cosine of v plus w given the values of cosine v and cosine w and the fact that v and w are angles in the first quadrant. Remember, to compute the cosine of a sum, we can't just add together the two cosines. That wouldn't even make sense in this case, because adding 0.9 and 0.7 would give something bigger than 1, and the cosine of something's never bigger than 1. Instead, we have to use the angle sum formula for cosine. So that goes cosine of v plus w equals cosine, cosine, minus sine, sine. Now I already know the cosine of v and the cosine of w, so I could just plug those in, but I have to figure out the sine of v and the sine of w from the given information. And one way to do that is to draw right triangles. So here I'm going to draw a right triangle with angle v and another right triangle with angle w. Since I know that the cosine of v is 0.9, I can think of that as 9 over 10, and I can think of that as adjacent over hypotenuse in my right triangle. So I'll decorate my triangle's adjacent side with the number 9 and the hypotenuse with 10. Similarly, since I know that the cosine of W is 0.7, which is 7/10, I can put a 7 on this adjacent side and a 10 on this hypotenuse. Now the Pythagorean theorem lets me compute the length of the unlabeled side. So this one is going to be the square root of 10 squared minus 9 squared. That's going to be the square root of 19. And here I have the square root of 10 squared minus 7 squared, so that's the square root of 51. I can now find the sine of V as the opposite over the hypotenuse, so that's the square root of 19 over 10, and the sine of W will be the square root of 51 over 10. Because we're assuming V and W are in the first quadrant, we know the values of sine need to be positive, so we don't need to jimmy around with positive or negative signs in our answers. We can just leave them as is. Now we're ready to plug into our formula. So we have that cosine of V plus W is equal to 0.9 times 0.7 minus the square root of 19 over 10 times the square root of 51 over 10. Using a calculator, this works out to a decimal approximation of 0.3187. This video gave the angle, sum, and difference formulas and used them to compute some values. To see a proof for why the sum formulas hold, please watch my other video. Remember the angle sum formulas? Those are the formulas for computing sine of A plus B and cosine of A plus B. I like to sing them. Sine, cosine, cosine, sine, cosine, cosine, minus sine, sine. This video gives a geometric proof of those formulas. There are many great proofs of the angle sum formulas, but I'd like to share with you one of my favorites for those who are interested. I'll write the angle sum formulas up here so we'll know what we're trying to prove. To prove these formulas, let me start by drawing an angle A and an angle B on top of that. Next, I'm going to draw a line perpendicular to this middle line, and I'm going to extend the top line until it meets that perpendicular, making a right triangle. Finally, I'll draw a rectangle around that right triangle that just touches its vertices. My rectangle is now divided up into 4 right triangles, and I'm going to choose units of measurement so that the hypotenuse of my middle triangle has length 1. Now let's stop for a minute to think about the angles of these other triangles. Since the top and the bottom edge of the rectangle are parallel lines, and this hypotenuse is a transversal, this angle up here must have the same measure as A plus B down here. Also, this skinny angle here must have the same measure as A down here, because this angle is 180 degrees minus 90 degrees minus this angle here, and this angle A is also 180 degrees, the measure of the angles in a triangle, minus 90 degrees minus that same angle. So I'll label this skinny angle with A. Next, let's figure out as many side lengths as we can. Based on the middle right triangle with hypotenuse 1, we know that this side length down here must be cosine of B, since adjacent over hypotenuse is cosine B. Similarly, this side length here must be sine of B, since opposite over hypotenuse is sine of B. Now we see that sine of B is the hypotenuse of this right triangle, which means that this little side here has measure sine A times sine B. That's because the opposite over the hypotenuse of this angle has to equal sine A. A similar argument shows that this side has to have measure cosine A times sine B. Please pause the video and take a moment to fill in the side lengths of this right triangle and this right triangle. You should be getting sine A cosine B, cosine A cosine B, sine of A plus B, and cosine of A plus B. But remember, we have a rectangle here, so the opposite sides have equal length. This tells us that sine of A plus B has to equal sine of A cosine of B plus cosine of A sine of B, which is exactly the first angle sum formula. Also, cosine of A plus B, which is this side length, is exactly the difference of this side length, cosine A cosine B, minus this side length, sine of A sine B. And that's the second angle sum formula. So I think that's a pretty great geometric proof of the angle sum formulas. This video gives formulas for sine of 2 theta and cosine of 2 theta. Please pause the video for a moment and see if you think this equation, sine of 2 theta equals 2 sine theta, is true or false. Remember that true means always true for all values of theta, where false means sometimes or always false. This equation is false because it's not true for all values of theta. One way to see this is graphically. If I graph y equals sine of 2 theta, that's like the graph of sine theta squished in horizontally by a factor of 1/2. On the other hand, if I graph y equals 2 sine theta, that's like the graph of sine theta stretched vertically by a factor of 2. These two graphs are not the same. So instead, we need a more complicated formula for sine of 2 theta. And that formula is sine of 2 theta is 2 sine theta cosine theta. It's not hard to see why that formula works based on the angle sum formula. Recall that sine of A plus B is equal to sine A cosine B plus cosine A sine B. Therefore, sine of 2 theta, which is sine of theta plus theta, is going to be sine theta cosine theta plus cosine theta sine theta, simply plugging in theta for A and theta for B in this angle sum formula. Well, sine theta cosine theta is the same thing as cosine theta sine theta, so I can rewrite this as twice sine theta cosine theta. That gives me this formula. There's also a formula for cosine of 2 theta, and that formula is cosine squared theta minus sine squared theta. Again, we can use the angle sum formula to see where this comes from. Cosine of A plus B is equal to cosine of A cosine of B minus sine A sine B. So if we want cosine of 2 theta, that's just cosine of theta plus theta, which is cosine theta minus sine theta sine theta by plugging in theta for A and B. This can be rewritten as cosine squared theta minus sine squared theta, which is exactly the formula above. Now there are a couple other formulas for cosine of 2 theta that are also popular. One of them is 1 minus 2 sine squared theta, and the other one is cosine of 2 theta is 2 cosine squared theta minus 1. You can get each of these two formulas from the original one using the Pythagorean identity. We know that cosine squared theta plus sine squared theta is 1, So cosine squared theta is 1 minus sine squared theta. If I plug that into my original formula, which I've copied here, so I'm plugging in, instead of cosine squared, I'm going to write 1 minus sine squared theta. I still have another minus sine squared theta, so that's the same thing as 1 minus twice sine squared theta, which is exactly what I'm looking for. Similarly, I can use the Pythagorean identity to write sine squared theta as 1 minus cosine squared theta. Again, I'll take this equation and copy it below, but this time I'm going to plug in for sine squared right here. So that gives me cosine of 2 theta is cosine squared theta minus the quantity 1 minus cosine squared theta. That simplifies to 2 cosine squared theta minus 1 after distributing the negative sign and combining like terms. So I have one double angle formula for sine of 2 theta, and I have 3 versions of the double angle formula for cosine of 2 theta. Now let's use these formulas in some examples. Let's find the cosine of 2 theta if we know that cosine theta is negative 1 over root 10 and theta terminates in quadrant 3. We have a choice of 3 formulas for cosine of 2 theta. I'm going to choose the second one because it only involves cosine of theta on the right side, and I already know my value for cosine theta. Of course, I could use one of the other ones, but then I'd have to work out the value of sine theta. So plugging in, I get cosine of 2 theta is twice negative 1 over root 10 squared minus 1, which simplifies to 2/10 minus 1, or negative 8/10, negative 4/5. Finally, let's solve the equation 2 cosine x plus sine of 2x equals 0. What makes this equation tricky is that one of the trig functions has the argument of just x, but the other trig function has the argument of 2x. So I want to use my double angle formula to rewrite sine of 2x. I'll copy down the 2 cosine x, and now sine of 2x is equal to 2 sine x cosine x. At this point, I see a way to factor my equation. I can factor out a 2 cosine x from both of these 2 terms. That gives me 1 plus sine x, and the product there is equal to 0. That means that either 2 cosine x is equal to 0 or 1 plus sine x is equal to 0. That simplifies to cosine x equals 0 or sine x is negative 1. Using my unit circle, I see that cosine of x is 0 at pi over 2 and 3 pi over 2, while sine of x is negative 1 at 3 pi over 2. There's some redundancy here, but my solution set is going to be pi over 2 plus multiples of 2 pi and 3 pi over 2 plus multiples of 2 pi. This video proved the double angle formulas. Sine of 2 theta is 2 sine theta cosine theta, and cosine of 2 theta is cosine squared theta minus sine squared theta. It also proved 2 alternate versions of the equation for cosine of 2 theta. This video is about the half angle formulas for computing cosine of theta over 2 and sine of theta over 2. Cosine of theta over 2 is either plus or minus the square root of 1 plus cosine theta all over 2. To figure out whether to use plus or minus, you need to know something about what quadrant the angle theta over 2 is. If you're expecting cosine theta over 2 to be negative, then you're going to need the negative sign. If you're expecting this cosine to be positive, then of course you want the positive sign, since the square root of something is always positive. Notice that this formula always makes sense because the inside of the square root sign is always going to be positive or 0, since cosine theta can't be any more negative than negative 1. We have a similar formula for sine of theta over 2, and that's plus or minus the square root of 1 minus cosine theta over 2. Notice that the formulas for both cosine of a half angle and sine of a half angle both have cosine in them. They just differ by the positive or negative sign in the inside of the square root. To see why these formulas hold, let's recall the formulas for double angles. We know that cosine of 2x is equal to 2 cosine squared x minus 1, or we can write cosine of 2x as 1 minus 2 sine squared of x. Of course, we can also write cosine of 2x as cosine squared x minus sine squared x, but this one won't be relevant to our discussion right now. So I'm going to start with this first formula, and I'm going to make the substitution theta equals 2x. That allows me to write cosine theta is 2 cosine squared theta over 2 minus 1, since if theta is 2x, then x is theta over 2. Now I'm going to solve for cosine of theta over 2. So I'll add 1 to both sides, divide both sides by 2, and take the square root of both sides. That gives me that cosine of theta over 2 is going to be plus or minus the square root of cosine theta plus 1 over 2, which is the formula we're looking for. I can carry a similar process out with the second formula. I'll substitute theta for 2x, which means that x is theta over 2. That gives me cosine theta is 1 minus 2 sine squared theta over 2. Now I'll solve for sine of theta over 2. I'll start by adding 2 sine squared theta over 2 to both sides. Next, I'll subtract cosine theta from both sides. Next, I'll divide both sides by 2. And finally, I'll take the square root of both sides. That gives me sine of theta over 2 is plus or minus the square root of 1 minus cosine theta over 2, which is the formula I was looking for. Now that we've got our formulas and know where they come from, let's use them in an example. Let's suppose that sine theta is 4/5 and theta is between pi over 2 and pi. That means it's in the second quadrant. We want to find the exact values of cosine theta over 2 and sine theta over 2. Since theta is between pi over 2 and pi, theta over 2 will be between pi over 4 and pi over 2. So theta over 2 is somewhere in the first quadrant. That means that cosine theta over 2 and sine theta over 2 will both be positive. Let me write down my half angle formulas, and I know I can ignore the negative version and just use the positive version. Now, unfortunately, I'm just given the value of sine theta, not cosine theta, so I can't plug in directly. First, I have to use this value to figure out what cosine might be. I'll draw a right triangle with angle theta, and since sine of theta is 4/5, I'll decorate the triangle with a 4 and a 5 on the hypotenuse. That means that this side length is going to be 5 squared, square root of 5 squared minus 4 squared, which is the square root of 9, which is 3. That means that cosine theta is going to be either plus or minus 3/5 because it's adjacent over hypotenuse. Now, since I'm in the second quadrant for my angle theta, cosine is actually going to be negative 3/5. Now I can plug into my formulas. I get that cosine of theta over 2 is going to be the square root of 1 minus 3/5 over 2. That simplifies to the square root of 2/5 divided by 2, which is the square root of 1/5, or 1 over the square root of 5. Sine of theta over 2 is the square root of 1 minus cosine theta, so that's 1 minus negative 3/5 over 2. That's the square root of 1 plus 3/5, or 8/5 over 2, the square root of 4/5 or 2 over the square root of 5. In this video, we found formulas for the cosine of a half angle and the sine of a half angle and used them in an example. Solving a right triangle means finding the lengths of all the sides and the measures of the angles given partial information. In this example, we're given the length of one side and the measure of one angle, plus we know the measure of this right angle is 90 degrees. We need to find the measure of the third angle, labeled capital A, and the lengths of the two sides, labeled lowercase b and lowercase c. To find the measure of angle A, let's use the fact that the measures of the three angles of a triangle add up to 180 degrees. So that means that 49 degrees plus 90 degrees plus A is equal to 180 degrees. So A is equal to 180 degrees minus 90 degrees minus 49 degrees, which works out to 41 degrees. To find the length of the side B, we have a couple possible options. We could use the fact that tan of 49 degrees, which is opposite over adjacent, is B over 23. So B is 23 times tan 49 degrees, which works out to 26.46 units. Alternatively, we could use the fact that tan of 41 degrees is 23 over B, since now, if we're looking at the angle here, 23 is our opposite and B is our adjacent. That's a little bit harder to solve algebraically, but we can write B tan 41 degrees equals 23, which means that B is 23 divided by tan 41 degrees. With a calculator, that works out again to 26.46. The reason we want to use tan in this problem and not, say, sine or cosine is because tan of, say, 49 degrees relates the unknown side that we're looking for, B, to the side that we know the measure of. If we had used sine instead, we would be saying that sine of 49 is B over C, and we'd have two unknowns, which would make it difficult to solve. Next, to find the side length C, we again have a few options. We could use a trig function again. For example, we could use the cosine of 49 degrees. That's adjacent over hypotenuse, which is 23 over C. Solving for C, we get that C is 23 over cosine 49, which works out to 35.06 units. Another option would be to use the Pythagorean theorem to find C. Since we know 23 squared plus B squared equals C squared, in other words, that's 23 squared plus 26.46 squared equals C squared, which means that C is the square root of that sum, which works out again to 35.06. To review, the ideas we used were the sum of the angles is equal to 180 degrees. We used facts like tangent of an angle being opposite over adjacent and similar facts about sine and cosine. And we used the Pythagorean theorem. This allowed us to find all the angles and side lengths of the triangle, knowing just the side length of one side and the angle of one of the non-right angles to begin with. In this next example, we don't know any of the angles except for the right angle, but we know two of the side lengths. To find the unknown angle theta, we can use the fact that cosine theta is adjacent over hypotenuse, so that's 10 over 15. Cosine is a good trig function to use here because this equation relates our unknown angle to our two known sides, so we just have one unknown in our equation to solve for. To solve for theta, we just take the cosine inverse of 10/15, which is 0.8411 radians, or 48.19 degrees. To find the measure of angle phi, we could use the fact that sine of phi is 10 over 15 and take sine inverse of 10/15, but probably a little easier is just to use the fact that these three angles add to 180 degrees. That tells us that phi plus 90 plus 48.19 is equal to 180, which means that phi is 41.81. Finally, we can find x either using a trig function or by using the Pythagorean theorem. To find it using a trig function, we could write down something like tan of 48.19 degrees is x over 10. To find it using Pythagorean theorem, we'd write down 10 squared plus x squared equals 15 squared. I'll use the Pythagorean theorem and find that x by doing the square root of 15 squared minus 10 squared. That gives me an answer of 11.18. Notice that we used many of the same ideas as in the previous problem. For example, the fact that the sum of the angles is 180, the Pythagorean theorem, and the trig functions like tan, sine, and cosine. We also used the inverse trig functions to get from an equation like this one to the angle. This video showed how it's possible to find the lengths of all the sides of a right triangle and the measures of all the angles given partial information. For example, the measure of one angle and one side, or from two sides. Recall that solving a triangle means finding all the lengths of the sides and all the measures of the angles from partial information. The law of cosines is a tool that can help us solve triangles that are not necessarily right triangles. Recall that the Pythagorean theorem says that for a right triangle, like this one, the length of the hypotenuse is related to the lengths of the sides by the formula c squared equals a squared plus b squared. I like to think of the law of cosines as a generalization of the Pythagorean theorem to triangles that are not necessarily right triangles. Loosely speaking, the law of cosines says that c squared is equal to a squared plus b squared plus a correction factor, where the correction factor depends on the size of the angle that's opposite to side C. For this first triangle, on the left, the angle that's opposite to side C is exactly a right angle. So we know that c squared is exactly equal to a squared plus b squared. But in this next triangle, the angle opposite to side C prime is a little bit less than a right angle. So we expect this side length C prime should be a little bit shorter than the side length C in the previous triangle that had the same side lengths A and B for its legs. Therefore, C prime squared should be less than A squared plus B squared, or in other words, C prime squared should equal A squared plus B squared minus a little bit. In this third triangle, the angle opposite C double prime is a little bigger than 90 degrees. So this side length C double prime should be a little bit longer than the side length C in the right triangle with the same size legs. So C double prime squared should be bigger than A squared plus B squared. We can write this as C double prime squared is equal to A squared plus B squared plus a little bit. The law of cosines says precisely what this little correction factor is. It says that for any triangle with sides A, B, and C, and angle capital C opposite side C, side C squared is equal to A squared plus B squared minus 2AB cosine angle C. Let's analyze what happens in this equation when angle C is equal to 90 degrees, less than 90 degrees, and greater than 90 degrees. If angle C is equal to 90 degrees, then cosine of angle C is equal to 0, So we have that c squared is equal to a squared plus b squared, the ordinary Pythagorean theorem. If, on the other hand, angle C is less than 90 degrees, then from the unit circle, we know that cosine of C is positive. So 2ab cosine C is a positive number, and we'll be subtracting a little bit from our a squared plus b squared, just like we saw in the picture. Finally, if angle C is bigger than 90 degrees, then we can see from the unit circle that cosine of C is negative. So 2ab cosine capital C is going to be less than 0, and we're going to be subtracting a negative number, which means we're actually adding a little bit, just like we saw in the third picture. When labeling a triangle, the convention is to use capital letters for the angles and lowercase letters for the side lengths, and to put side A opposite angle A, and so on. When we wrote the law of cosines on the previous page, we wrote c squared equals a squared plus b squared minus 2ab cosine angle C. But it doesn't matter which side we call A, which side we call B, and which side we call C. All that matters is that this angle is opposite to this side and between these two sides. So we could have just as easily written a squared is equal to b squared plus c squared minus 2bc cosine A. All we've done is replace c with a with b, and b with c in our labeling scheme. Or instead, we could put the b squared on the left side and write b squared equals a squared plus c squared minus 2ac cosine b. We can use whichever of these three forms is most convenient for the problem at hand. Let's use the law of cosines to find all the side lengths and angles in this triangle. By convention, I'll call the side opposite to angle A little a, and the side opposite angle B little b. Notice that we know two side lengths and the angle between them. So that's an SAS, side angle side, triangle. If we write down the law of cosines with the unknown side c squared on the left side, then we have all the values for the variables on the right side. So let's plug them in. I'll use a calculator in degree mode to find that c squared is equal to 44.44. Taking the square root, I get that c is equal to 6.67. Next, I'll use the law of cosines to find the angle B. I'll need to use a version of the law of cosines that has cosine B right here. That's the version that has little b squared on the left side, and goes b squared equals a squared plus c squared minus 2ac cosine b. I can plug in values for all my side lengths, and now I can solve for cosine b. To do that, I'll subtract 8 squared and 6.67 squared from both sides, and now I'll divide both sides by negative 2 times 8 times 6.67. Using a calculator, this gives me that cosine of b is equal to negative 0.1172. The negative value of cosine indicates that my angle B must be greater than 90 degrees, which agrees with the figure. Next, I can take cosine inverse of both sides to get that B is equal to cosine inverse negative 0.1172, which works out to 96.73 degrees. The last thing I need to do is solve for angle A. I could use the law of cosines again and work out angle A just like I worked out angle B here. But a simpler thing to do is to use the fact that the sum of the three angles equals 180 degrees. In other words, A plus 37 degrees plus 96.73 degrees equals 180 degrees. So A is going to be 180 minus 37 minus 96.73, which works out to 46.73 0.27 degrees. In the previous example, we were given two sides and the angle between them. In this example, instead, we're given three side lengths. So I'll call this an SSS, side, side, side triangle. We need to find all three angles. Although there are a lot of computations involved, the ideas are the same as in the previous problem. To find angle capital C, we need the form of the law of cosines that has cosine of C on the right side and little c on the left side. To find angle A, we need the form of the law of cosines that has cosine A on the right side and little a on the left side. And to find angle B, we need the form of the law of cosines that has cosine of B on the right side and little b squared on the left side. For each of these three equations, I'll plug in the side lengths, solve for the cosines, and use inverse cosine to find my angles. Notice that my three angles, 60 degrees, 32.20 degrees, and 87.79 degrees, add up to just almost 180 degrees. The difference is just due to round-off error. In fact, I could have saved myself some work by just finding the measure of angle C and the measure of angle A, and then subtracting them from 180 degrees to get the measure of angle B. In this video, we stated the law of cosines and used it to solve some triangles. The law of cosines can be thought of as the Pythagorean theorem with a correction factor to account for triangles that aren't right triangles. Recall that solving a right triangle means finding all the lengths of the sides and all the measures of the angles from partial information. The law of cosines is a tool that can help us solve triangles that are not necessarily right triangles. Recall that the Pythagorean theorem says that for a right triangle, like this one, c squared is equal to a squared plus b squared. I like to think of the law of cosines as a generalization of the Pythagorean theorem to triangles that are not necessarily right triangles. Loosely speaking, the law of cosines says that c squared is equal to a squared plus b squared plus a correction factor, where the correction factor depends on the size of the angle that's opposite size c. In this first triangle on the left, the angle opposite to side C is a right angle. So we know that c squared is equal to exactly a squared plus b squared. But in the next triangle, the angle opposite to side C prime is a little bit less than a right angle. So this side C prime should be a little shorter than a squared plus b squared. I'll write c prime squared is equal to a squared plus b squared minus a bit. In this third triangle, since the angle opposite to side C double prime is a little bit bigger than 90 degrees, this side length should be a little bit bigger than a squared plus b squared. So I'll write it as a squared plus b squared plus a little bit. The law of cosines says exactly what this little correction factor is. It says that for any triangle with sides A, B, and C and angle capital C opposite to side C, c squared is equal to a squared plus b squared minus 2ab cosine of angle C. Notice that if the angle C is less than 90 degrees, cosine of C is going to be a positive number. And so we'll be subtracting a positive quantity, just like we saw in the picture above. If, however, angle C is bigger than 90 degrees, then cosine of C is negative. So by subtracting 2ab cosine C, we're actually adding a little bit, and we get a longer side, as in this picture. When labeling a triangle, the convention is to use lowercase letters for the side lengths and uppercase letters for the angles, and to put angle A opposite side A, and so on. When we wrote the law of cosines on the previous page, we wrote c squared equals a squared plus b squared minus 2ab cosine c. But it doesn't matter which side we call a, which side we call b, and which side we call c. All that matters is that this angle is opposite to this side and between these two sides. So we could have just as easily written a squared equals b squared plus c squared minus 2bc cosine a, or b squared equals a squared plus c squared minus 2ac cosine b. We can use whichever of these three forms is most convenient for the problem at hand. Let's use the law of cosines to find the side lengths and angles of this triangle. By convention, I'm going to call the side opposite angle B side little b, and the side opposite angle A side little a. Since we know two side lengths and the angle between them, we have all the information on the right side of the law of cosines. So I'll plug that in and use a calculator in degree mode to find that c squared equals 44.44. Taking the square root, I get that c equals 6.67. Next, I'll use the law of cosines to find the angle b. I'll need to use a version of the law of cosines that mentions cosine of angle b here. So it'll need to mention side length little b here. So that'll be the form b squared on the left. I'll get a squared plus c squared minus 2ac cosine b on the right. I'll plug in values for all my side lengths. And now I can solve for cosine b by subtracting 8 squared and 6.67 squared from both sides, and now dividing both sides by negative 2 times 8 times 6.67. Using a calculator, this gives me that cosine of b is equal to negative 0.1172. The negative value of cosine indicates that my angle b must be greater than 90 degrees, which agrees with the picture. Next, I can take cosine inverse of both sides to get that b is equal to cosine inverse of negative 0.1172, which works out to 96.73 degrees. The last thing I have to do is solve for angle A. I could use the law of cosines again and work it out just like I did here for angle B, but a simpler method is to just use the fact that the sum of the three angles is 180 degrees. So A must be 180 degrees minus 37 degrees minus 96.73 degrees. This works out to 46.27 degrees. In the previous example, we were given two sides and the angle between them. In this angle, we're given instead three side lengths, and we need to find all three angles. Although there are a lot of computations involved, the ideas are the same as in the previous problem. To find angle capital C, we need the form of the law of cosines that has cosine of capital C on the right side. To find capital B, we need to use the form of the law of cosines that has cosine of b on the right side and little b on the left side. So it'll be b squared equals a squared plus c squared minus 2ac cosine b. And to find angle A, we need little a squared on the left side so that we'll get cosine of angle A on the right side. For each of these three equations, I'll plug in the side lengths, solve for the cosine of the angle, and use inverse cosine to find my angles. Notice that my three angles, 60 degrees, 87.79 degrees, and 32.20 degrees, add up to almost exactly 180 degrees. It's just a tiny bit off due to round-off error. In fact, I could have saved myself some work by just finding the measure of angle C and the measure of angle B, for example, and then subtracting their sum from 180 degrees to get angle A. In this video, we stated the law of cosines and used it to solve some triangles. The law of cosines can be thought of as the Pythagorean theorem with an adjustment factor to account for triangles that aren't right triangles. The law of sines is a tool that can be used to solve triangles that are not necessarily right triangles. It's especially useful when we know two angles and one side. And it can also be used in the situation where we know two sides and an angle that's not between them. The law of sines says that for a triangle with angles A, B, and C, opposite to sides lowercase a, b, and c respectively, the sine of angle A divided by the length of side A is equal to the sine of B over B, which is also equal to the sine of C over C. Notice that we're taking the sine of the three angles and dividing by the three opposite side lengths. Suppose we know that angle A is 55 degrees, angle C is 67 degrees, and side B is 20 degrees. We want to solve the triangle, that is, find the lengths of the other sides and the measure of the third angle. Since we know two angles already, we can find the third angle by subtracting from 180 degrees. So angle B is 58 degrees. Now I can use the law of sines to find my remaining side lengths. To find side A, I'll use the fact that sine of angle A over side length A is equal to sine of angle B over side length B. Since I already know three of these quantities, angle A, angle B, and side length B, I can plug in and solve for the unknown side length A. To solve, I'll multiply both sides by A, and then multiply both sides by 20 over the sine of 58 degrees. That gives me that A is equal to 20 sine 55 over sine 58, which works out to 19.32. Please pause the video and use the same method to find side length C. This time, we need to involve sine of C and side length C in our equation, and we could use either the B's or the A's since they're both known for the other side. I'll plug in values as I can and solve for C. C works out to 21.71. In the previous example, we used the law of sines to find the side lengths of a triangle because we already knew the angles. In this next example, we're given some side lengths and we're going to need to solve for some angles. This can be tricky because when we write down the law of sines and start solving for an angle, we first solve for sine of the angle. But there can be two plausible angles that both have the same sign. For example, if sine of the angle happens to be 1/2, then the angle could be either 30 degrees or 150 degrees. In some cases, this can lead to two possible triangles that both have the conditions given. When this happens and there are two possible solutions, I call this an ambiguous case. With that warning, let's figure out the details of this example. Plugging in my given information into the law of sines, I'll focus on this portion of the equation where there's only one unknown to solve for. First, I'll solve for sine of A, which is 8 times sine 40 degrees over 7, which works out to 0.7346. From the unit circle, I can see that there'll be two possible angles with this sine, one in the first quadrant and one in the second quadrant. If I take sine inverse of both sides of my equation, I get the solution in the first quadrant, which is 47.27 degrees. Since this angle right here is 47.27 degrees, so is this angle here, and so the angle that I want in the second quadrant I can get by going 180 minus 47.27 degrees, which works out to 132.73. One of these possible angles is an acute angle, the other one an obtuse angle, but both are possible configurations. I'll sketch the possible triangles. In both triangles, side length A and B are the same, and angle B is the same, but everything else is different. We can continue to solve for the other angle and side in each case. In the left side, I'll call this case 1, we can solve for angle C by taking 180 degrees minus angle B minus angle A. That gives us an angle just over 90 degrees, 92.73 degrees. Now we can use either the law of sines or the law of cosines to find the final side length C. I'll use the law of sines again. So I'll plug in the value of angle C into this part of my equation and solve for C to get C equals sine 92.73 degrees times 7 over sine 40 degrees, which works out to 10.88. For the right-hand triangle, we can carry out the same steps to get angle C, and now plug into the law of sines to get side length C. We've finished solving for the two possible triangles with these given side lengths and angle. In this video, we used the law of sines to solve a triangle in two different situations. In the first situation, we had two angles and the side between them, so that's an ASA triangle for angle, side, angle. In that situation, we ended up just using the law of sines to solve for side lengths, and there was no ambiguity. In the second situation, we had a triangle where we knew two side lengths and an angle that was not between them. So I'll call that SSA. And in that case, we did find two possible triangles that would work. The SSA situation doesn't always give two possible triangles. Sometimes when you go through the two cases and figure out all the other angles and side lengths, you'll get an impossible situation. An angle, for example, that has to be negative because the other two angles add up to more than 180 degrees. But you do have to be on the lookout for two possible triangles when you're solving a triangle with the SSA information given. This video describes some of the features of a parabola: its vertex, focus, and directrix. I want to start by finding the equation of all points that are equidistant, the same distance, from a point 0p on the y-axis and the horizontal line y equals negative p. I'm assuming here that p is positive for starters. Certainly the origin will be among those points, as it has a distance of p from the point and p from the line. But the other points on the x-axis will be closer to the line than they are to the point. So if I want the set of points that are the same distance from the point and the line, that's going to be a curve that curves upwards, something like this. So for example, a point out here will be the same distance from the point as it is from the line. So our intuition is suggesting that this set of points should be the shape of a parabola. Let's confirm this with some algebra. If we take an arbitrary point with coordinates x, y, its distance from the point 0p is given by the distance formula, x minus 0 squared plus y minus p squared. Its distance from the line, y equals negative p, is just given by its difference in y coordinates. So that's going to be y minus negative p, or y plus p. Let me set these two quantities equal to each other. and simplify. I can square both sides to get on the left x minus 0 squared, which is the same thing as x squared, plus y minus p squared equals y plus p squared. Now I'll distribute out. That gives me x squared plus y squared minus 2py plus p squared equals y squared plus 2py plus p squared. The p squareds cancel out, as do the y squareds, and I'm left with x squared equals 4py after moving this negative 2py to the other side. I could also write this as y equals 1 over 4p x squared, and you might recognize this as the standard parabola y equals x squared transformed by vertically stretching or shrinking it by this factor of 1 over 4p. You might recall that this lowest point of the parabola is called the vertex. This point here is called its focus, and the line here is called the directrix. Notice that the number p in this equation represents the distance between the vertex and the focus, and also represents the distance between the vertex and the directrix line. For this reason, if you're interested in the focus and the vertex, this form of the equation might be more useful than the equivalent form, something like y equals ax squared, where that distance p is more hidden. Now, so far, we've just considered the case when p is greater than 0. Let's look for a moment at what happens when p is less than 0. Then, when we draw the point 0p, it's going to be below the x-axis, and the directrix, y equals negative p, is going to be above the x-axis, because we're taking the negative of a negative number makes it a positive y value. Our parabola will also be upside down. All the algebra works out the same. It's just in our equation, this coefficient of y will now be a negative number instead of a positive one. Or if we write it in this other form, which might be more familiar, our coefficient of x squared will be negative instead of positive, which signifies that the parabola is pointing down. Since p is now a negative number, if we want to talk about distances, we should write absolute value of p instead of p. Next, let's turn things sideways by looking at the equation for all points equidistant from a point p0 on the x-axis. Here we're assuming, for starters, that p is bigger than 0, and a vertical line at x equals negative p. Our intuition suggests that this should be a parabola pointing sideways. And we can work out the same algebra steps to get an equation for it. Starting with an arbitrary point x, y, the distance from the point p0 is going to be given by x minus p squared plus y minus 0 squared. The distance from the line, x equals negative p, is going to be given by the difference in x-coordinates, so that's going to be x minus negative p, or just x plus p. I'll set these two distances equal to each other, square both sides like before, and simplify. This gives me the equation y squared equals 4px, which I could also rewrite as x equals 1 over 4p y squared, or x equals a y squared, where my a corresponds to my 1 over 4p. Once again, if p is negative, then my parabola will be pointing the opposite direction, but my equation will still be the same. It'll just have a negative coefficient of x instead of a positive one, the negative number being hidden inside this variable p. As before, the absolute value of p gives me the distance between the vertex and the focus, and also gives me the distance between the vertex and the directrix. Now let's find the equation of a parabola with a vertex at some arbitrary point hk instead of the origin, assuming that the parabola opens up or down. If the parabola had its vertex at the origin, we know it would be given by the equation x squared equals 4py, or I could rewrite that as y equals 1 over 4p x squared. So this parabola should just be shifted to the right by h and up by k. From transformations of functions, we know we can accomplish this by sticking a x minus h on the inside and putting a plus k on the outside. In other words, we have y minus k equals 1 over 4p times x minus h squared, or we can write this as x minus h squared equals 4p times y minus k. So this is the original with the vertex at the origin, and here is the transformed by shifting right and up to have a vertex at hk. Notice that the equations are exactly the same. It's just you stuck in a minus h and a minus k near the x and near the y. This transformed parabola will have its focus a distance of p up from the vertex. So that's going to be the point h, k plus p. And it's going to have its directrix at a distance p down from the vertex. So that's going to be the line y equals k minus p. Everything's the same for this other parabola pointing downwards. We just have p is negative in that case. The same story holds for the parabolas pointing right and left. The original equation, y squared equals 4px, gets transformed when we shift the parabola over into y minus k squared equals 4p x minus h. This time, the vertex is a distance p to the left or right of my vertex, so here it would be h plus p k, and the directrix would be shifted over by p also from the vertex, so this would be the vertical line x equals h minus p. It works the same way when the parabola is opening left instead of right. It's just in this case p is negative. Let's use this information to find the equation of a parabola with vertex at 2, 4 and focus at negative 1, 4. I'll start with a quick sketch, which will help me see how the parabola is lined up. So here's the vertex at 2, 4, and the focus is at negative 1, 4. So here's the focus here. Now, since the parabola always hugs its focus, that means that this parabola must be pointing left and looks something like this. The directrix is going to be on the other side of the parabola, the same distance as the distance between the vertex and the focus. Since this distance is a distance of 3, 2 minus negative 1 is 3, the directrix must be 3 units over here to the right, and so that would be the line x equals 5. Since my parabola is open to the left, I know I need to use the form of the equation y minus k squared equals 4p x minus h, where hk is the vertex, so that's 2, 4. I also know that p is going to be negative, and since the absolute value of p represents the distance between the vertex and the focus, I know that p must be negative 3. So filling in all these numbers, I get y minus 4 squared equals 4 times negative 3 times x minus 2. I'll simplify that to y minus 4 squared equals negative 12 x minus 2. In this video, we looked at special forms of the equation for a parabola. The forms y minus k squared equals 4p x minus h, and x minus h squared equals 4p y minus k. In these equations, hk represents the vertex, and p's absolute value gives the distance between the vertex and the focus, and between the vertex and the directrix. Parabolas in this form are opening right if p is bigger than 0 and left if p is less than 0, and parabolas in this form are opening up if p is bigger than 0, and down if p is less than 0. This video is about ellipses. Recall that a circle can be defined as a set of points whose distance from a fixed point is a constant. An ellipse can be defined as a set of points such that the sum of the distances from two fixed points is a constant. The two fixed points are called focuses or foci, and the sum of the distances to the two foci is the total length of the string, which is held constant as I draw the ellipse. Let's examine the features of an ellipse in more detail. In these pictures, the two black dots are the focuses or foci. The red line segment that cuts through the middle of the ellipse in the long direction and passes through the foci is called the major axis. The line segment that cuts through the middle of the ellipse in the shorter direction is called the minor axis. And the 2 points at the tips of the ellipse, where the major axis actually touches the ellipse, are called the vertices. An ellipse could be elongated in any direction, but we'll only consider ellipses that are elongated either in the horizontal direction or the vertical direction. Let's find the equation of an ellipse whose foci are at negative c, 0, and c, 0, and whose vertices are at negative a, 0, and a, 0. This will be an ellipse that's elongated in the horizontal direction. For any point xy on the ellipse, the sum of the distance from xy to the first focus plus its distance to the second focus has to be some constant. And in fact, it turns out that constant has to equal 2a. I'll show you why. If you look at this point right here on the far right tip of the ellipse, its distance from the first focus is going to be 2c plus a minus c. And its distance from the second focus is just going to be a minus c. If you add up c plus a minus c plus a minus c, you get exactly 2a. So let me write out my formulas for distances. The distance from a point xy to the first focus, the point negative c, 0, is going to be the square root of x minus negative c squared plus y minus 0 squared. And the distance from xy to the second focus, the point c, 0, is going to be the square root of x minus c squared plus y minus 0 squared. That sum needs to add up to 2a. After a fair amount of algebra, this simplifies to the expression a squared minus c squared, x squared plus a squared y squared equals a squared times a squared minus c squared. If we let b squared equal a squared minus c squared, then we can rewrite this as b squared x squared plus a squared y squared equals a squared b squared, and dividing both sides by a squared b squared, this gives us the form of the equation for the ellipse x squared over a squared plus y squared over b squared equals 1. Since we got b squared as a squared minus c squared, it follows that b is less than a. In fact, b is half the length of the minor axis. In other words, this point right here is the point 0b, and this point is the point 0, negative b. To see why this is true, let's draw these two right triangles. The sum of the side lengths that I've drawn has to be the total length of the string, so that equals 2a, which means each of these side lengths must be a. Now the base of this triangle is c, so by the Pythagorean theorem, this height squared must be a squared minus c squared. Since b squared is defined as a squared minus c squared, this height must be b. To summarize, for a number a bigger than b, the equation x squared over a squared plus y squared over b squared equals 1 represents an ellipse that's elongated in the horizontal direction, whose major axis terminates in the points minus a0 and a0, and whose minor axis terminates in the points 0b and 0 minus b. Its foci are at the points negative c0 and c0, and the relationship between a, b, and c is that b squared is a squared minus c squared. Equivalently, if we add c squared to both sides and subtract b squared from both sides, we can write c squared equals a squared minus b squared. The way I remember this is that the biggest of the three numbers a, b, and c is definitely going to be a. Since a is half the length of the major axis, which is bigger than half the length of the minor axis, and definitely bigger than the length between the origin and one of the focuses. Since a is the biggest, and we have a Pythagorean theorem relationship between a, b, and c, the equation must be b squared plus c squared equals a squared, which can be rearranged to either of these two equations. Now what happens instead if we have a bigger than b still, but this time we're dividing y squared by the bigger number squared and x squared by the smaller number squared? Well, this basically reverses the roles of x and y in my equation, and so we end up with the major axis on the y-axis, stretching between the points 0a and 0 negative a, whereas the minor axis is going to be along the x-axis, going in between negative b0 and b0, and the foci are going to be here on the y-axis again. So in this case, my ellipse is elongated in the vertical direction. Our previous ellipses were centered at the origin, but what if the ellipse is centered instead at an arbitrary point, hk? Well, then we need to shift everything over by h in the horizontal direction and k in the vertical direction, so instead of the equation x squared over a squared plus y squared over b squared equals 1, we're going to have x minus h squared over a squared plus y minus k squared over b squared equals 1, where a is bigger than b. That's for an ellipse elongated in the horizontal direction. If we want an ellipse elongated in the vertical direction, we'll still take a bigger than b, but we'll reverse the roles of x and y, so this becomes x squared over b squared plus y squared over a squared equals 1 for the center at the origin. And to shift it over, we get x minus h squared over b squared plus y minus k squared over a squared equals 1. I'll draw some pictures below. With some thought, we can label key points. For example, this vertex must be shifted over by an amount a, since a is half the length of the major axis, so it'll have coordinates h plus a, k, whereas this vertex will be h minus a, k. This point up here should be h, k plus b, and this one h, k minus b. The foci are at h plus c, k, and h minus c, k. We can label the points on the ellipse that's elongated vertically similarly. Let's write the equation of the ellipse drawn below, and then we'll find its foci. Its major axis is in the vertical direction, right here. Its top vertex is at the point 4, 3, and its bottom vertex is at the point 4, negative 9. Its center is halfway between its two vertices, which is right here at the point 4, negative 3. Finally, I can read off the points at the end of the minor axis. So this one is at 9, negative 3, and this one is at negative 1, negative 3. Since my ellipse is elongated vertically, I know I have an equation of the form x minus h squared over b squared plus y minus k squared over a squared equals 1, with a bigger than b. My center is my point hk, and that's equal to 4, negative 3. A is half the length of the major axis, so that's the vertical distance between this point and this point. I can just take the difference of y coordinates and see that a is equal to 6. B is half the length of the minor axis, so looking at the difference in x coordinates of these 2 points, I see that b is equal to 5. Throwing that all into my equation, I get that x minus 4 squared over 5 squared plus y plus 3 squared over 6 squared equals 1. The foci are going to be somewhere along the major axis, somewhere above and below the center. To figure out how far they are, I need to use the fact that c squared is equal to a squared minus b squared. So in this case, c squared is 6 squared minus 5 squared, which is 11, which means that c is the square root of 11, which is a little bit bigger than 3. So the two foci are distance of square root of 11 above and below the center, and so they'll have coordinates of 4, negative 3 plus the square root of 11, and 4, negative 3 minus the square root of 11. This video detailed the anatomy of an ellipse, including its major axis, its minor axis, its vertices, and its foci. This video is about hyperbolas. You might recall that an ellipse is the set of points x, y, such that the sum of the distances between x, y, and two fixed points, called the foci, is a constant. Well, a hyperbola is a set of points x, y, such that the difference of the distances between x, y, and each of two fixed points, called the foci, is a constant. In this picture on the left, the two blue lines are the two branches of the hyperbola. The two red points are the focuses, or foci. So for a point xy on the hyperbola, if I look at the distance from xy to one focus and the distance from xy to the other focus, the difference of those two distances will be the same no matter which point xy on the hyperbola that I choose. If I draw a line between the two foci, that line is called the transverse axis. In this left picture, we have a vertical transverse axis, and the hyperbola itself reminds me of a person lying down horizontally. Now in the right picture, our transverse axis between the two foci is horizontal, and the blue hyperbola itself kind of reminds me of a person standing up vertically. It's possible for a hyperbola to be oriented other ways besides horizontally and vertically, but we'll only consider horizontal and vertical orientations in this video. If you look at where the transverse axis intersects the blue branches of the hyperbola, you'll find these 2 points. Those points are called the vertices. Notice that the vertices are the 2 points on the 2 branches that are closest to one another. The point halfway between the 2 vertices, it's also halfway between the 2 foci, is called the center of the hyperbola. The 2 black dotted lines that I've drawn that form an X are not actually part of the hyperbola. They're called the asymptotes. And you can think of them as guidelines for drawing the hyperbola because the hyperbola gets closer and closer to these asymptotes but doesn't cross them. We'll talk more about the asymptotes later. Let's find the equation of a hyperbola with foci at negative c0 and c0 and vertices at negative a0 and a0. This hyperbola will have its center at the origin. From the distance definition of hyperbola, we know that if we have a point xy on the hyperbola, then if we take the distance from that point to the first focus and the distance to the second focus and subtract them, we should get a constant. We're always taking the positive difference here, so if we're on the right branch, we'll take the distance to the left focus minus the shorter distance to the right focus, and if we happen to be on the left branch, then we would take the longer distance to the right focus minus the shorter distance to the left focus. When we do the differences that way, we should always get the same number, and in fact, that difference should equal 2a. I'll show you why. The reason is, if I take my point to be this vertex here, then its distance to this focus is exactly c minus a, because c is bigger than a. And this distance to that focus is going to be, well, let's see, this is a, and this is c minus a, so that different distance will be a plus c minus a. Now I'm going to do the difference, a plus c minus a minus c minus a. That simplifies to a plus c minus c plus a, which is 2a. Now I'll focus on a point on the right branch, and I'll actually write a formula for its distance to this point. That's the distance formula. It's going to be x minus negative c squared plus y minus 0 squared. That's the longer distance. Now I subtract the shorter distance, which is the distance to this focus, and there the distance formula gives me x minus c squared plus y minus 0 squared. That should always equal 2a for any point on that right branch. I'll clean up the inside of the square roots a little bit. After that, a chunk of algebra, which I won't do here, allows you to simplify this equation to c squared minus a squared times x squared minus a squared y squared equals a squared times c squared minus a squared. Since this expression c squared minus a squared is appearing a couple times here, I'm going to give it a new name. I'm going to let b squared be c squared minus a squared. Now I can rewrite my equation as b squared x squared minus a squared y squared equals a squared b squared, and dividing both sides by a squared b squared yields the equation x squared over a squared minus y squared over b squared equals 1. In this equation, notice that a represents the distance from the center to a vertex. The quantity c is not directly in this equation, but it's related to a and b by this equation, which can also be rewritten as c squared equals a squared plus b squared, or if you prefer, a squared equals c squared minus b squared. I remember this one, and remember that c, which is the distance from the center to the focus, is the largest of the three quantities a, b, and c. So you might be wondering, well, what does b represent? Well, I'm going to draw a box whose center is at the center of my hyperbola that stretches out in a from either direction, left, right, and stretches up by b in either direction, up and down. It turns out that the corners of such a box will be exactly on these two asymptote lines. In other words, the slope of this asymptote, its rise over its run, is b over a. And for this asymptote that's sloping downwards, its rise over its run is negative b over a. So I can actually write the equations of the asymptotes for this hyperbola centered at the origin as y equals b over ax and y equals negative b over ax. We did all this work for a standing up hyperbola with its transverse axis oriented horizontally. Let me rearrange things, and we'll see what changes if the hyperbola is oriented the other way. In this case, where we have a vertical transverse axis, the roles of x and y are completely switched. So our equation, which we could derive the same way, becomes y squared over a squared minus x squared over b squared equals 1. We still have the same formulas, c squared equals a squared plus b squared, and the two related formulas, b squared equals c squared minus a squared, and a squared equals c squared minus b squared. A is still the distance from the center to the vertex, and c still represents the distance from the center to a focus. Now our box will extend up and down by a units, and left and right by b units. So this time, the slope of the asymptote the rise over the run is going to be a over b for the line that's sloped up, and negative a over b for the line that's sloped down. This means our asymptotes, which go through the center at the origin, will be given by the equations y equals a over bx and y equals negative a over bx. I want to point out that in this notation, a is going with x in one form of the equation and y in the other form of the equation, but it always goes with the positive term, the term that's added instead of subtracted, whereas b goes with the negative term, the term that's subtracted. Which term is positive, either the x squared or the y squared, determines the orientation of the hyperbola this way or that way. So far, we've been considering only hyperbolas centered at the origin, and we had these two equations for them. If we center at an arbitrary point hk instead, we just subtract h from the x term and subtract k from the y term. The graphs are shifted over by h and up by k, and to get to the vertices, we just start at the center and go left and right by a, or up and down by a, depending on which way the hyperbola is oriented. So the vertices here are at h plus a k and h minus a k, whereas over here the vertices are at h k plus a and h k minus a. To get to the focuses, we have to go over by c or up and down by c, where c squared equals a squared plus b squared. Finally, the asymptotes still have the same slopes as before, but this time they have to go through the center, which is at hk instead of 0, 0. Their equations are going to be given by y minus k equals b over a x minus h, and y minus k is negative b over a x minus h, or with the other orientation, the analogous thing, y minus k equals a over b x minus h, and y minus k equals a over b negative a over b x minus h. We've done all the abstract theory. Let's do one example with numbers. If we're given this hyperbola, we can read off its center as 6, negative 3. Since the x term is positive, I'm going to let a be the square root of 4, and b will be the square root of 25. Since the x term is positive and the y term is negative, the hyperbola is going to be oriented standing up, like this, with a horizontal transverse axis. The distance from the center to each vertex is given by the number a, which is 2. So the left vertex will have coordinates 4, negative 3, and the right vertex will have coordinates 8, negative 3. To find the foci, I need to figure out c squared, which is a squared plus b squared, or 4 plus 25, 29. So c is the square root of 29. I'll sketch ballpark position of my foci here, and the coordinates are going to be at, let's see, the center is 6, so 6 minus square root of 29, same y coordinate of negative 3, and 6 plus square root of 29, negative 3. Finally, the asymptotes will form an x going through the center with slope given by b over a, which is 5 halves, and negative b over a, negative 5 halves. The equations for those lines will be y plus 3, coming from the center, equals 5 halves x minus 6, and y plus 3 equals negative 5 halves x minus 6. This gives a decent rough sketch of the hyperbola. If I want to be a little more accurate, I could also plot some points by plugging in values of x and solving for y, or vice versa. In this video, we gave 2 equations for hyperbolas. Which one you use depends on how the hyperbola is oriented. A has to do with the distance between the center and the vertex. the number c, which can be figured out from the equation c squared equals a squared plus b squared, is going to represent the distance from the center to the focus. And b and a together help determine the slope of the asymptotes. This video introduces the idea of polar coordinates. Polar coordinates give an alternative way of describing the location of points on the plane. Instead of describing a point in terms of its x and y coordinates, those are the Cartesian coordinates of the point, when using polar coordinates, we instead describe the point in terms of a radius r and an angle theta. R is the distance of the point from the origin, and theta is the angle that radius line makes with the positive x-axis. Let's plot these points given in polar coordinates. So the 8 here is the value of the radius, and the negative 2/3 pi is the value of the angle, theta. The negative angle means that I need to go clockwise from the positive x-axis, instead of counterclockwise like I normally would for a positive angle. So here, a negative 2/3 pi means that I need to go to this line right here, and the 8 for the radius means I need to go 8 lines out from the origin, so my point should be around right here. The next point has a radius of 5 and an angle of 3 pi. The angle of positive 3 pi means that I go counterclockwise starting at the positive x-axis. Here I've gone around by 2 pi, and here I've got an extra pi to make 3 pi. Now the radius of 5 means I need to go 5 units out from the origin, so that puts me about right here. Notice that I could have also labeled this point with the polar coordinates of 5 pi. There's more than one way to assign polar coordinates to a point. The next point has an angle of pi over 4 and a radius of negative 12. The negative radius means that I need to jump to the other side of the circle before I plot the point. In other words, instead of plotting the point at an angle of pi over 4 and a radius of 12, which would be about right here, I go to the opposite side of the circle and plot it at the same distance from the origin, but 180 degrees or pi radians around the circle over here. Now I could have also labeled this point using a positive radius of 12 and using an angle of pi over 4 plus pi, or 5 pi over 4. And in general, a point with polar coordinates of negative r theta means the same point as the point with polar coordinates r theta plus pi. Adding pi just makes us jump around to the opposite side of the circle. To convert between polar and Cartesian coordinates, it's handy to use the following equations. First, x is equal to r cosine theta, y is equal to r sine theta, r squared is equal to x squared plus y squared, which means that r is plus or minus the square root of x squared plus y squared, and tangent theta is equal to y divided by x. Let's see where these equations come from. If we draw a point with coordinates x, y, and draw lines to make a right triangle, the height of that triangle is y, the length of the base is x, and the hypotenuse has length r. Theta is the measure of this interior angle. From trig, we know that cosine theta is equal to adjacent over hypotenuse, so that's x over r, which means that x is equal to r cosine theta. Similarly, sine theta is opposite over hypotenuse, that's y over r, which means that y is equal to r sine theta. That gives us the first two equations. The Pythagorean theorem tells us that x squared plus y squared is equal to r squared, and that gives us the third equation. Finally, tangent theta is opposite over adjacent, so that's y over x, which is the fourth equation. To convert 5 negative pi over 6 from polar to Cartesian coordinates, we just use the fact that x equals r cosine theta and y equals r sine theta. So in this case, x is equal to 5 times cosine of negative pi over 6. That's 5 times square root of 3 over 2. And y is equal to 5 sine negative pi over 6. So that's equal to negative 5 halves. To convert negative 1 from Cartesian to polar coordinates, we know that negative 1 and negative 1 are our x and y values, so we need to use the fact that r squared is x squared plus y squared, that is, r squared is negative 1 squared plus negative 1 squared, or 2. Also, tangent theta is y over x, so that's negative 1 over negative 1, or 1. Now there's several values of r and theta that satisfy these equations. R could be square root of 2, or negative the square root of 2, and theta could be pi over 4, or 5 pi over 4, or we could add multiples of 2 pi to either of these answers. But not all combinations of r and theta get us to the right point. The point with Cartesian coordinates negative 1, negative 1 lies in the third quadrant. But if we use a theta value of, say, pi over 4 and an r value of square root of 2, that would get us to the first quadrant. So instead, we need to use the polar coordinates of square root of 2 and 5 pi over 4, or, if we prefer, negative square root of 2 and pi over 4. We could also add any multiple of 2 pi to either of these values of theta and get yet another way of representing the point in polar coordinates. This video talked about polar coordinates and converting in between Cartesian coordinates and polar coordinates using some familiar equations from Trig. This video introduces the idea of parametric equations. Instead of describing a curve as y equals f of x, we can describe the x-coordinates and y-coordinates separately in terms of a third variable, t, usually thought of as time. So we can write x as a function of t and y as a separate function of t. This is especially useful as a way to describe curves that don't satisfy the vertical line test and therefore can't be described traditionally as functions of y in terms of x. A Cartesian equation for a curve is an equation in terms of x and y only. Parametric equations for a curve give both x and y as functions of a third variable, usually t. The third variable is called the parameter. As our first example, let's graph the parametric equations given here on an xy coordinate axis. We'll do this by finding x and y coordinates that correspond to the same value of t. For example, when t is negative 2, you can calculate that x, by plugging in negative 2 for t, gives you 5, and y, when you plug in negative 2 for t, gives you 8. Please pause the video for a moment and fill in some additional values of x and y for some additional values of t. Your chart should look like this, and when we plot the xy pairs and connect the dots, we get something like this. Notice that this point over here corresponds to a t value of negative 2, and this point over here corresponds to the t value of 2. So if we think of t as time, we're traversing the curve in this direction. To find a Cartesian equation for this curve, we need to eliminate the variable t from these equations. One way to do this is to solve for t in one equation, say the first equation. So 2t is equal to 1 minus x, which means that t is 1/2 minus x over 2. Then we can plug that expression for t into the second equation and get y equals 1/2 minus x over 2 squared plus 4, which simplifies to the quadratic equation y equals 1/4 x squared minus 1/2 x plus 17/4. Let's try some more examples. A table of values for the first example helps us draw the familiar graph of a circle of radius 1. This should come as no surprise, since the equations x equals cosine t and y equals sine t are familiar from trig as a way of describing the x and y coordinates of a point on the unit circle. Notice that when t equals 0, our curve lies on the positive x-axis, and as t increases from 0 to 2 pi, we traverse the curve once in the counterclockwise direction. A Cartesian equation for this unit circle is given by the equation x squared plus y squared equals 1. This follows from the trig identity cosine squared t plus sine squared t equals 1 by substituting in x for cosine t and y for sine t. Please pause the video for a moment to graph the second curve and rewrite it as a Cartesian equation. A table of values should help you see that the graph is again a unit circle, but this time, as t increases from 0 to 2 pi, we actually traverse the circle twice in the clockwise direction. I'll draw this with a double arrow moving clockwise. The Cartesian equation for this graph is still x squared plus y squared equals 1. And so we found two different parameterizations for the same graph on the xy axis. Let's take a look at the third equation. There's no interval of values specified for t here, so let's just assume that t can be any real number. Now, as t ranges from negative infinity to infinity, our y values, which are given by cosine t, oscillate between 1 and negative 1. Our x values are always the square of our y values. So the graph of this curve has to lie on the graph of x equals y squared, which is a sideways parabola. But our parametrically defined curve doesn't cover this whole parabola. Remember that y is given by cosine of t, so y can only range between negative 1 and 1. And so we're only getting the portion of the parabola that I shade in here. As t varies from, say, 0 to pi, I traverse this parabola one time. And then as t goes from pi to 2 pi, I go back again in the other direction. And as t continues to increase, I traverse this parabola infinitely many times. The Cartesian equation for this curve is the equation x equals y squared, with the restriction that y is between negative 1 and 1. We've seen several examples where we went from parametric equations to Cartesian equations. Now let's start with a Cartesian equation and rewrite it as a parametric equation. In this example, y is already given as a function of x. So an easy way to parameterize this curve is to just let x equal t, and then y is equal to the square root of t squared minus t, substituting in t for x. The domain restriction in terms of x just translates into a restriction in terms of t. I call this the copycat parameterization, since we've successfully introduced the new variable t, but t just copies whatever x does. In the second example, we could try setting x equal to t. Then we get 25t squared plus 36y squared is equal to 900. And solving for y, we'd have y squared equals 900 minus 25t squared over 36. So y is plus or minus the square root of this quantity. This is a very awkward looking expression. In fact, y is not even a function of t here because of the plus and minus signs. So let's look for a better way to parameterize this curve. Because of the x squared and the y squared, this equation is a good candidate for parameterizing using sine and cosine. In fact, if we divide both sides of the equation by 900, we get 25x squared over 900 plus 36y squared over 900 is equal to 1, which simplifies to x squared over 36 plus y squared over 25 is equal to 1. If I rewrite this as x over 6 squared plus y over 5 squared equals 1, then I can set x over 6 equal to cosine of t and y over 5 equal to sine of t, and I can see that for any value of t, x over 6 and y over 5 will satisfy this equation simply because cosine squared plus sine squared equals 1. This gives me the parameterization x equals 6 cosine of t, y equals 5 sine of t, which is a handy way to describe an ellipse. As a final example, let's describe a general circle of radius r and center hk. For any point x, y on the circle, we know that the distance from that point xy to the center of the circle is equal to r. So using the distance formula, we know that the square root of x minus h squared plus y minus k squared has to equal r. Squaring both sides, this gives us the equation for the circle in Cartesian coordinates. So for example, if our circle has radius 5 and has center at the point -3, 17, then its equation would be x minus -3, that's x plus 3 squared, plus y minus 17 squared is equal to 25. One way to find the equation of a general circle in parametric equations is to start with the unit circle and work our way up. We know that the unit circle, with radius 1, centered at the origin, is given by the equation x equals cosine t and y equals sine t. If we want a circle of radius r centered around the origin instead, then we need to expand everything by a factor of r. So we multiply our x and y coordinates by r. If we now want the center to be at hk instead of at the origin, then we need to add h to all our x coordinates and add k to all our y coordinates. This gives us the general equation for a circle in parametric equations to match the Cartesian equation above. We can write our same example circle in parametric equations as x equals 5 cosine t minus 3, y equals 5 sine t plus 17. In this video, we translated back and forth in between Cartesian equations and parametric equations, with a special emphasis on the equations for circles. This video is about the difference quotient and the average rate of change. These are topics that are related to the concept of derivative in calculus. For a function y equals f of x, like the function who's graphed right here, a secant line is a line that stretches between 2 points on the graph of the function. I'm going to label this x value as a and this x value as b. So this point here on the graph is going to have an x value of a and a y value given by f of a. The second point will have x value b and y value f of b. Now the average rate of change for a function on the interval from a to b can be defined as the slope of the secant line between the 2 points a f of a and b f of b. In symbols, that slope m is the rise over the run, or the change in y over the change in x, which is the difference in y coordinates, f of b minus f of a, over the difference in x coordinates, b minus a. So this is the average rate of change. To put this in context, if, for example, f of x represents the height of a tree, and x represents time in years, then f of b minus f of a represents a difference in height, or the amount the tree grows, and b minus a represents a difference in years, so a time period. So this average rate of change is the amount the tree grows in a certain time period. For example, if it grows 10 inches in 2 years, that would be 10 inches per 2 years, or 5 inches per year would be its average rate of change, its average rate of growth. Let's compute the average rate of change for the function f of x equals square root of x on the interval from 1 to 4. So the average rate of change is f of 4 minus f of 1 over 4 minus 1. Well, f of 4 is the square root of 4, f of 1 is the square root of 1. So that's going to be 2 minus 1 over 3, or 1/3. Instead of calling these two locations on the x-axis a and b, this time I'm going to call the first location just x, and the second location x plus h. The idea is that h represents the horizontal distance between these two locations on the x-axis. In this notation, if I want to label this point on the graph of y equals f of x, it'll have an x-coordinate of x and a y-coordinate of f of x. The second point will have an x-coordinate of x plus h and a y-coordinate of f of x plus h. A difference quotient is simply the average rate of change using this x plus h notation. So a difference quotient represents the average rate of change of a function f of x on the interval from x to x plus h. Equivalently, the difference quotient represents the slope of the secant line for the graph of y equals f of x between the points with coordinates x, f of x, and x plus h, f of x plus h. Let's work out a formula for the difference quotient. Remember that the formula for the average rate of change could be written as f of b minus f of a over b minus a, where a and b are the two locations on the x-axis. But now I'm calling, instead of a, I'm using x, instead of b, I'm using x plus h, so I can rewrite this average rate of change as f of x plus h minus f of x over x plus h minus x. That simplifies a little bit on the denominator, because x plus h minus x, I can cancel the x's, and I get the difference quotient formula, f of x plus h minus f of x over h. The quantity h on the denominator looks like a single entity, but it still represents a difference in x values. Let's find and simplify the difference quotient for this function given. First, I'll write down the general formula for the difference quotient. That's f of x plus h minus f of x over h. I'm going to compute f of x plus h first. I do this by shoving in x plus h everywhere I see an x in the formula for the function. So that's going to give me 2 times x plus h squared minus x plus h plus 3. Notice how I use parentheses here. That's important because I need to make sure I shove in the entire x plus h for x, so the entire x plus h needs to be subtracted, not just the x part, so the parentheses are mandatory. Similarly, the parentheses here signal that the entire x plus h is squared, as it needs to be. I'm going to go ahead and simplify a bit right now. I can multiply out the x plus h squared. I can go ahead and distribute the negative sign. So if I multiply out, I'm going to get x squared plus xh plus hx plus h squared. Now I can distribute the 2 to get 2x squared plus 2xh plus 2hx plus 2h squared minus x minus h plus 3. These two terms are actually the same. I can add them up to get 4xh. And I think that's as simple as I can get that part. Now I'm going to write out f of x plus h minus f of x. So that's going to be this thing right here, minus f of x. Again, I need to put the f of x formula in parentheses to make sure I subtract the whole thing. I'll distribute the negative. And now I notice that a bunch of things cancel out. So the 2x squared and the minus 2x squared add to 0. The minus x and the x add to 0. And the 3 and the minus 3 add to 0. So I'm left with 4xh plus 2h squared minus h. Finally, I'll write out the whole difference quotient by dividing everything by h. I can simplify this further because notice that there's an h in every single term of the numerator. If I factor out this h times 4x plus 2h minus 1 divided by h, these two h's cancel, and I'm left with a difference quotient of 4x plus 2h minus 1. This difference quotient will become important in calculus when we calculate a difference quotient for smaller and smaller values of h, eventually letting h go to 0 and ending up with an expression that has no h's in it and represents the derivative or slope of the function itself. In this video, we use the formula f of b minus f of a over b minus a to calculate an average rate of change, and the related formula f of x plus h minus f of x over h to calculate and simplify a difference quotient.